Are planets nothing more than rock and gas in different spheres orbiting in different suns, or does each world, like a sealed book, carry within it a puzzle that stubbornly resists the reader, a riddle that only patience, curiosity, and a certain kind of imagination can begin to unpick? This is not a question about geology or astrophysics alone. It is a question about attention. The deeper the scrutiny, the stranger the object. A planet viewed from a distance is a painted coin, a color, a smear of clouds, a hint of continents. Viewed closer, it becomes a landscape. Closer still, it becomes a biography, layer upon layer of events, accidents, rhythms, and perhaps intentions. The act of looking changes the world into a text. What does the text say? What could it possibly conceal beneath the strata? There is a particular kind of silence that hangs over deep time questions. It is not empty, it is dense with absence. Ice cores and sedimentary beds, magnetic stripes on the ocean floor, microscopic inclusions in crystal lattices. These are not stories told in the present tense. They are archives. They speak in the slow grammar of epochs, in punctuation marks the scale of centuries and the pauses of glacial cycles. To read them requires translation, instruments, models, a patience that outlives routine human time. The disquiet comes from realizing that most of what a planet has ever done is written in this slow script, and most of it is obscure by default. The closer the lens, the more the page reveals its smudges. On Earth, there are examples of this archival nature everywhere. A shore that seems ordinary is a palimpsest of tides, storms, and organisms. Rocks that look inert hide. A choreography of minerals born under pressures that once existed only in the belly of a mountain now. Ground into dust, the crust is a ledger of impacts, eruptions, drownings, uplifts, and quiet seasons of sedimentation. Each layer is a thin, neutral witness. If one imagines for a moment a different history, a history in which sentient builders once shaped coastlines, erected cities, harvested ore, and left behind artifacts and waste, the mind is compelled to ask, what traces would survive? How would they read in the language of strata, isotopes, and erosion? Here the narration becomes speculative, but disciplined. The logic of erasure is not fanciful. Geological processes are relentless editors. Plate tectonics rearranges the very pages of a planetary book, shoving sections into mountain range presses and then shaving them down into sediment that the sea carries away. Subduction grinds crust into the mantle, effectively recycling matter and burying record as a librarian shreds and rebinds a manuscript. Erosion smooths sharp edges, fills cavities, and buries cities in meters of soil. Acid weathering, corrosion, salt crystallization. These are not mere inconveniences. They are time's hands rubbing ink until letters blur. In short, geological time, measured in millions of years, evidence of complex surface activity can be diluted, dismantled, and finally dissolved. Yet erasure is not complete absence. Even where structures crumble, subtle signatures persist. Consider the interplay of chemistry and scale. Metallurgy leaves isotopic fingerprints. The extraction and heating of ores change local geochemistry in ways that can survive burial. The presence of anomalous concentrations of rare elements, of non-natural alloys, or of isotopic ratios inconsistent with background geological processes would stand out like a single odd sentence in a vast textbook. Organic molecules, too, can be preserved under the right conditions, tracked and altered by mineral matrices, fossilized within amber-like resin analogues, or sequestered in anaerobic sediments. Organic waste, synthetic polymers, and plastics, if they are durable enough, could survive for geologically significant periods. In forms unrecognizable to the non-specialist, yet clear to a trained analyst. There is a second archive, subtler still, indirect consequences. Energy-intensive civilizations must leave thermal footprints. Large-scale agriculture or urbanization alters sediment transport and erosion patterns, changes pollen distributions, and shifts the relative abundance of microbial communities. A massive technological activity might leave a global chemical signature, a spike in greenhouse gases, a layer of soot, a change in the oxygen to carbon balance of the atmosphere. Such signals, smeared to the atmosphere and then recorded in ice cores and deep-sea sediments, are like a planetary fever chart. They are not direct fossils of tools or monuments, but they are the systemic after-effects of behavior writ on the planet's chemistry. Another possibility is the tale told by geometry itself. Natural processes can and do create striking regularity, basalt columns, snowflake symmetries, ripple marks in sand, but sustained patterns of large-scale regularity. Especially materials that do not ordinarily manifest that order could serve as an index of agency. Straight lines, right angles, repeating modules on a scale that could not be plausibly produced by known abiotic processes would be suspiciously meaningful. The problem is, such geometries are also remarkably vulnerable. They are the first to be eroded, the first to be overwhelmed by biological colonization, and the first to be buried or reworked. The planet tends to prefer organic mess over engineered order when given time. Time is the essential protagonist in the story. To think in geological time is to scale down human drama to a single line in a margin and then to feel the vertigo of perspective. Humans can be both astonished and humbled by the numerical enormity of deep time, billions of years in which continents assemble and break apart, in which climates swing from blistering warmth to icebound silence, in which life itself morphs through unimaginable forms. There is a necessary melancholy in this orientation. The rose-tinted certainty of present-day life is dwarfed by the slow pulse of planetary processes. The hubris of permanence appears comic. The planet offers an implacable rewrite. What rises, falls. What is built is reclaimed. And yet, if the planet is a palimpsest, then gaps in the text invite hypotheses. With each improvement in observational dexterity, higher resolution satellite imagery, more sensitive spectrometers, ground-penetrating radar, more refined isotopic analysis, new candidates for anomalies arise. They are seldom conclusive. A line in the desert might be a fossilized riverbed, a tectonic fault, or the remains of construction. A chemical spike in an ice core might be volcanic, cosmic, or anthropogenic. The detective work requires not the confidence of an eyewitness, but the humility of the archivist, cataloging possibilities, weighing likelihoods, and always conceding to uncertainty. This humility is the emotional core of the inquiry. There is a peculiar mixture of hope and apprehension in the human stance toward planetary riddles. Hope, because even a faint sign could overturn assumptions and reveal a heritage of previously unimagined complexity. Apprehension, because any imagined narrative might collapse under tighter scrutiny, and because the implications of earlier intelligence of long cycles of rise and fall complicate moral and existential self-understanding. To entertain the possibility of advanced, long-lost activity on Earth is to confront the contingency of human achievements and the tenuousness of cultural memory. It is to ask whether grandeur can be ephemeral and whether knowledge can be undone by geological patience. There is an aesthetic dimension to this as well. Some of the most compelling evidence in planetary science is not a neat artifact, but a pattern that arrests the gaze. The alternating laminae of a varved lake, the regular chirality of magnetic reversals recorded in oceanic crust, the unexpected abundance of certain elements in a deep-sea core, these are the universe's marginalia. They invite interpretation. The mind loves patterns, but the scientist loves patterns that survive attempts to falsify them. The discipline of speculation is to imagine boldly, and then to subject those imaginations to rigorous skepticism. Worlds beyond Earth amplify the stakes. A planet with a thick, rust-colored atmosphere, or a moon with a subsurface ocean warmed by tidal flexing, becomes more than a distant curiosity. It becomes a potential archive of alternate histories. On Mars, a reader peers at valley networks and layered deposits and asks whether fluvial chapters were once written there. On Europa or Enceladus, the analysis shifts. The book might be bound not in rock but in ice, with plumes serving as torn pages flung into space. Each solvent, silicate crust, icy shell, metallic core, shapes the kind of evidence that might persist. The question is universal. What traces of complex processes, including intelligence, could survive each planetary environment? And how would those traces differ from the signatures of geology and chemistry? The answer, necessarily, is contingent. Preservation is a function of environmental conditions and time. On a dry, cold world, hardened organic molecules may last longer. On a wet, tectonically active planet, the surface is a recycling floor. On an icy moon, processes that would be destructive on Earth can act as conservators, encapsulating organic matter in crystalline prisons. The imagination must therefore move, like a good scientist, from general to particular, from a broad hypothesis to environment-specific expectations. There is also a methodological humility in this orientation. The search for ancient techno-signatures, for artifacts or systemic imprints of past intelligence is not a hunt for the obvious. It is a forensic enterprise. Forensic science on geological scales is messy, probabilistic, and often inconclusive. It requires interweaving multiple strands of evidence, morphological irregularities, chemical anomalies, energy budgets, ecological shifts. The absence of incontrovertible artifacts does not falsify the hypothesis. The presence of plausible anomalies does not prove it. What it does do is enrich our understanding of what to look for and how to recognize the faint footprints of agency in the vast noise of planetary processes. This approach changes the way the planet is perceived. Instead of a backdrop, Earth becomes an archive with margins, smudges, erasures, and palimpsests. Instead of a stage, it is an ongoing process. The emotional tenor of this perspective is not triumphalism, but reverence. There is a quiet awe in contemplating the layers upon layers of work, natural and perhaps artificial, that accumulate and then fade. There is also a gripping suspense, the possibility that a small, overlooked signal, a peculiar concentration, a regularity carved deep in a non-obvious substrate, might tip the balance of interpretation. To look closer is to invite paradox. The more granular the observation, the more the planet resists simple narratives. A valley is not only a valley, it is a product of climate, lithology, tectonics, and perhaps human labor. A chemical signature is not only a spike, it is a composite of volcanic outgassing, biomass turnover, cosmic deposition, and possibly industrial effluent. Unraveling these threads requires models capable of integrating disparate timescales and processes. It requires instruments that can extract weak signals from strong backgrounds. And, crucially, it requires a narrative that can tolerate not knowing as an enduring state rather than a temporary problem to be solved. The central image that lingers is that of a book returned to after centuries of neglect. Its cover is weathered, its pages eaten by mildew, some sections lost to the elements. Yet when a reader opens it, fragments of text become legible, marginalia hint at revisions long forgotten, annotations, smudged and cryptic, invite speculative reading. The planet, in this metaphor, is both author and editor, cosmic forces acting both to compose and to erase. The work that remains is an invitation to sift, to measure, to hypothesize, and above all, to accept that the most interesting answers might be the ones that reframe the questions. Finally, the question circles back, unresolved but deepened. Are planets mere aggregates of matter and motion? Or are they complex records, repositories of processes that may include episodes of intelligence, episodes now faint as moth wings? The answer may ultimately be less a binary and more a spectrum. Some worlds may be straightforward, dominated by geochemistry with only incidental surprises. Others may be palimpsests of astonishing complexity, their surface narratives altered beyond recognition by cataclysms, only to be rediscovered in the subtle hues of isotopic fractionation or the stubborn geometry of buried structures. This opening meditation does not promise resolution. It promises curiosity and a method, to seek anomalies, to refine tools, to read the slow script of ice and stone with imagination and restraint. It asks the listener to inhabit a particular mood, a blend of smallness before the vast sweep of time, of temporary stewardship, and of persistent wonder at what might yet be waiting, faint and patient, in the margins of the world's long book. What does it mean that worlds begin as dust? How does a yawning, anonymous cloud of microscopic grit become the stubbornly particular object that will outlast empires and fossilize a dozen? Geologic stories, and why, in a scheme that seems to prefer scales and patterns, does a planet as small and peculiar as Mercury exist at all? A dense, iron-rich spheroid perched like a punctuation mark close to the sun, refusing to fit the neat expectations of planetary formation? The simplest, most compelling answer that astronomers offer is also the most poetic. Planets are the byproducts of a rotating disk. Around a newly ignited star, leftover gas and dust spread into a flattened band of matter. That protoplanetary disk is not homogeneous. It is layered in temperature and chemistry, threaded by magnetic fields, stirred by turbulence, and sculpted by radiation. Over a few million years, an eye blink in cosmic time, the microscopic grains in that disk collide, stick, and grow. From adhesive van der Waals kisses to gentle sintering, dust becomes pebbles, pebbles become boulders, and boulders, in the merciless arithmetic of gravity, begin to gather mass and identity. The disk is that first sentence of the planetary book, a messy, dynamic preface whose tensions will determine much of what follows. There is a cadence to this growth. In the inner, hotter regions of the disk, only the most refractory materials, metals and silicates, can condense. Farther out, beyond the so-called snow line, volatile ices can accumulate and rapidly increase the available solid mass. This variation in composition and density seeds the diversity of outcomes. Small rocky worlds form where the heat forbids ice. Giant planets coalesce where ice multiplies the available solids, and the nascent core can attract a massive gaseous envelope before the disk dissipates, but the details are less deterministic than a textbook can convey. The disk is a living laboratory where timing, local chemistry, turbulence, and stochastic collisions conspire to produce a panoply of worlds. The standard narrative of accretion is itself a scene, innumerable collisions, some constructive, some destructive. At first, collisions glue particles together, sticky surfaces, electrostatic attraction, and low-speed encounters allow growth. But as objects become larger, gravity usurps adhesion. Planetesimals, tens to hundreds of kilometers across, begin to shepherd nearby material. A runaway growth phase ensues. The largest bodies grow disproportionately fast, sweeping up material and carving gaps in the disk. Eventually, an oligarchic regime follows, with a handful of planetary embryos dominating different radial zones. These embryos can clear their neighborhoods, stir planetesimals into violent encounters, or lock into orbital resonances. Migration, the radial movement of bodies due to interactions with the gas, rearranges the architecture. A planet born at one location may, over a few 100,000 years, drift dozens of millions of kilometers inward or outward. The disk lifetime, typically a few million years, is a hard deadline. After the gas is gone, migration halts, and the remaining choreography is played out by collisions and gravitational scattering. Seen this way, the formation of a planetary system is equal parts choreography and chaos. A handful of parameters: mass of the disk, metallicity of the star, temperature gradients, magnetic activity, bias outcomes, but small differences can be amplified. Two nearly identical disks could yield markedly different systems because of a single, violent collision at a crucial time. The result is the bewildering diversity observed among exoplanets. Compact systems of many tightly packed super-Earths, hot Jupiters stranded close to their stars, and lonely gas giants in wide orbits. The solar system emerged with a particular arrangement that, in hindsight, looks peculiar. Small, rocky inner planets, a belt of debris, and gas giants farther out. But exceptions and anomalies lie within that arrangement, and Mercury is one of them. Mercury's oddity is both anatomical and narrative. It is extraordinarily dense for a planet its size. Its mean density implies a core that takes up a far larger fraction of its volume than Earth's core does. The mantle is thin, the silicate shell is reduced. Early hypotheses invoked a simple, dramatic event, a titanic impact in the chaotic, late stages of accretion. A glancing blow so violent that it stripped away much of Mercury's original mantle, blasting silicate material into space and leaving an iron-rich remnant. The image is cinematic, a molten, incandescent collision, debris arcing into solar orbit, a stripped husk cooling in the glare of the young sun. In many ways, this hypothesis satisfied an aesthetic itch for a single dramatic explanation. Large impacts do occur. They explain other peculiarities in planetary history, from the Earth-Moon system to the scars on Mars. But the geochemical evidence complicates the neatness of that story. Data returned by the Messenger spacecraft revealed that Mercury retains significant amounts of volatile elements, potassium, sulfur, sodium, relative to expectations for a body that had lost its silicate blanket to energetic stripping. Volatile retention is a sign that formation might have been less cataclysmically scorching than the purely impact-driven model required. Furthermore, the specific isotopic ratios and surface minerals hinted at chemical processes in the early inner disk that could have produced metal-rich planetesimals in the first place. In other words, Mercury might not be only a survivor of flame and blow, it might be a product of a particular environment in the protoplanetary disk. A second class of explanations therefore invites a quieter, more distributed causality. Instead of a single giant collision, Mercury's composition could reflect the way solids sorted themselves in the inner disk. Processes like photophoresis, the force exerted on particles by uneven heating from starlight, can preferentially push lighter, less refractory grains outward while leaving metal-rich grains closer in. Magnetic forces and pressure gradients in the inner disk, coupled with aerodynamic drag on different-sized particles, can produce radial fractionation, zones enriched in iron-rich chondrules, regions deprived of volatiles. Pebble accretion models complicate the picture further. Small pebbles drift inward under gas drag and are collected efficiently by growing embryos. If the inner disk provided a steady rain of refractory pebbles depleted in volatile ices, The mass that coalesced there could naturally skew toward metal-rich compositions without invoking an erasing blow. There is also the possibility of chemical reduction, a term that hides a vivid process. In an oxygen-poor environment, iron tends not to oxidize and bind into silicates, instead remaining metallic. If mercury accreted in an area of the nebula where oxygen was scarce relative to other elements, more iron would be free to form a massive core. The result would be a planet-born iron-heavy, not manufactured that way by violence afterwards. This hypothesis aligns with the presence of unexpected volatile abundances, the body formed from a reservoir that already had unusual chemistry, not by being baked and stripped. Another angle points to timing and dynamical context. If Mercury formed very early, before Jupiter and Saturn had fully settled into their orbits, the inner disk environment might have been subject to more intense shepherding of solids. The formation timing affects the amount of available material and which reservoirs feed the growing embryo. Later migration of the gas giants could have cleared or perturbed nearby building blocks, leaving an undersized mantle around a disproportionately massive core. Or, during a chaotic late stage, repeated erosive collisions could have eroded the mantle incrementally, not a single catastrophic strike, but a suite of smaller, stripping events that cumulatively produced Mercury's present state. These differing sequences, early accretion in a refractory-rich lane, subtle sorting processes, incremental erosion, or catastrophic impact are not mutually exclusive. The truth might be a braided combination, each thread contributing to the final weave. Beyond Mercury, this puzzle of origin illuminates a larger philosophical tension in planetary science. How much of a planet's identity is set by initial conditions, and how much is the result of contingency? The disk's chemistry and structure provide bias. They are the grammar. Collisions, migrations, and late-stage interactions are the narrative choices that can redirect meaning. For an observer interested in reading planetary palimpsests, this tension is intimate. A planet's surface tells a story shaped by both its creation and its history. Distinguishing the two is a delicate exegesis. Observations of exoplanetary systems add another layer of urgency and humility. The universe presents many architectures that our old models did not predict. Kepler and subsequent missions revealed compact systems of multiple super-Earths and mini-Neptunes orbiting close to their stars, often packed more tightly than Mercury, Venus, Earth, and Mars combined. The prevalence of such systems suggests that inward migration and close-in accumulation of solids are common. If migration is frequent, then Mercury-like misfits might be the fossil record of broader disk dynamics rather than isolated oddities. Yet observational biases complicate inference. Detecting small, Mercury-sized planets at moderate distances is hard, and so our statistical sample is necessarily skewed towards certain sizes and orbital periods. In some cases, Mercury analogs may be common but hidden. In others, their rarity might point to a real process that disfavors their formation or long-term survival. Either outcome speaks to the complexity of planetary systems and underscores the limits of simple narratives. The mystery of Mercury also carries an existential cadence. To think about a tiny, iron-heavy planet close to its star is to feel the faint echo of time's indifference. If worlds can be remade by a single impact or by the slow sorting of grains in a disk, then planetary identities are not immutable. The deep past permits erasure and reinvention at scales that dwarf human history. For an age-old planet like Earth, this is a sobering reminder. Its present condition is a contingent consequence of billions of years of dynamic processes. The origin story of planets is therefore not a comforting Genesis myth, but a study in contingency, vulnerability, and improbable survival. Scientifically, the pathway forward is methodical and multi-pronged. Improved observations of protoplanetary disks, with instruments capable of resolving sub-AU scales in nearby star forming regions, can refine models of particle sorting and pebble flux. Laboratory studies of high-temperature chemistry under varying redox conditions help constrain plausible compositions. Isotopic analyses of Mercury and other planetary bodies would provide tighter constraints on source regions and processes. Missions like Bepi-Colombo, now en route to Mercury, promise additional data to test hypotheses, surface composition, magnetic field details, and gravity constraints will sharpen the narrative. Each piece of evidence is a single marginalia in the planetary book. Alone, it is suggestive. Together, they can begin to form a coherent paragraph. The interpretive method is worth pausing on. Planetary science in this regime is forensic, not dogmatic. It requires constructing scenarios and then hunting for discriminating signatures. Would an impact event leave a particular distribution of isotopes? Would a fractionated inner disk produce a gradient of refractory to volatile ratios across the surviving inner planets? Would incremental erosion leave different surface textures and crustal thicknesses than a single blow? The detective work is less about proving a single story and more about eliminating inconsistent explanations. It is a practice in humility, mirroring the epistemic caution demanded by reading the deep time book introduced earlier. Finally, the question returns to the original image: dust to planet, chaos to order, oddities like Mercury as footnotes or chapter headings. The puzzle of small, strange worlds is not merely an academic curiosity, it is a lens on how order emerges from noise. If a planet as seemingly modest as Mercury can force a re-evaluation of models, then every constant, every assumption, must be treated as provisional. The origin of planets is a study in process, in probabilities, and in the patient accumulation of evidence. It is a reminder that the cosmos writes with a hand equal parts law and whimsy. For the listener, there is a human reaction baked into this scientific unfolding, awe tempered by modesty. The formation of planets is at once ordinary, a natural consequence of physics operating on gas and dust, and extraordinary, a source of singular worlds, each with its own irreducible story. Mercury's stubborn mismatch with expectations is not a failure of science, it is an invitation. It invites better instruments, more nuanced models, and a willingness to accept that the narrative of planetary origin can hold multitudes. Above all, it invites patience, the same patience required to read the slow script of ice cores and sediment, to decode the marginalia left by an ancient author who composes in epochs. In that patience lies a peculiar consolation. The protoplanetary disk's grainy chaos, when given time and a few simple rules, will produce patterns, planets, moons, belts that are both predictable in their physics and surprising in their details. The small, heavy worlds like Mercury are part of that surprise, empirical reminders that the Book of Planets resists reductive summaries. Their existence keeps the reader engaged, turning pages slowly, awaiting the next marginal clue that will rearrange the sentence and perhaps, momentarily, the meaning. Why does a planet that cups the sun so closely carry within it so disproportionate an iron heart? That question drifts like a persistent ember through the study of planetary origins. It is both simple, a mismatch between expectation and measurement, and capacious, because it forces a confrontation with the ways the early solar system sorted matter, with violent collisions and with subtle forces that act on grains of dust. Mercury is not merely a scorched pebble, it is an argument in miniature about contingency, chemistry, and the long memory of processes that played out when the sun was young. Close to its star, Mercury experiences extremes that strip away any comforting analogy with the temperate scenes of Earth. The day side, when the sun stares directly, reaches temperatures that melt many metals on the surface, while the night side, turned away, can fall into depths of cold that preserve volatiles only in the most tenuous forms. There is no substantial atmosphere to redistribute heat. The planet is a body of pronounced thermals, registering the sun's attention with the brutal honesty of surface temperature contrasts. This diurnal brutality produces an immediate sense of otherness. The surface is not a place in equilibrium, but a stage where flux and absence have been recorded for billions of years. That record is not silent. From orbit and from the sparse landforms it displays, Mercury speaks in a language of scars and gradients. Long, cliff-like features, lobate scarps, wrinkle the crust, testimony to a planet that has cooled and contracted. Smooth volcanic plains hint that, despite proximity to the sun, the world once possessed enough internal heat and volcanism to resurface itself in places. The surface is peppered with craters of every size, each an archival syllable of bombardment. There are also enigmatic, high-reflectance pits, the so-called hollows, whose freshness and spectral properties point to processes still ongoing, volatile substances sublimating or being spotted away by solar radiation, leaving behind bright scars on the regolith. Around Mercury, a ghostly exosphere, not an atmosphere in the classical sense, but a thin veil of atoms liberated by micrometeoroid impacts and the solar wind, whispers of the present-day interactions between sun and rock. Sodium, potassium, calcium. These elements are intermittently visible, blown into ephemeral clouds and then stripped away again. The planet, close to the sun, endures a steady erosion by radiation and particles. It is at once fossil and freshly eroded manuscript. The most disquieting observation, however, lies beneath the surface chemistry and radiometric constraints. Mercury is anomalously heavy for its size. Its average density implies a core that occupies a markedly larger fraction of its volume than on Earth. The silicate mantle is thin. To a geologist trained in terrestrial expectations, Mercury's proportions are a riddle. How did it acquire so much metal and so little rock? That single question branches into a thicket of possible narratives, each plausible, each with implications that extend into the processes that shaped not only Mercury but interplanetary architecture more broadly. One family of explanations is dramatic and cinematic. In the late stages of accretion, when planetary embryos orbited in a dense ballet and collisions were common, Mercury might have suffered a cataclysmic impact. A glancing high-energy collision could have sheared off a large fraction of an original silicate mantle, ejecting it into space where it would either be accreted elsewhere or fall into the sun, leaving behind an iron-rich remnant. The image is memorable: a molten shower, a rebounding core, a body spun and scarred. Such scenarios are consistent with the rudimentary logic of giant impacts elsewhere in the system. They explain the moon's origin, and they fit within the chaotic late-stage dynamics known to be common. They are also attractive because they reduce a complex history to a single, narrative-rich event. Yet a cinematic solution, tidy as it is, fails to account for certain chemical subtleties. Spacecraft observations, most notably from NASA's MESSENGER mission, revealed Mercury's surface composition to be richer in volatile elements, sulfur, sodium, and others, than a body that had been violently stripped to an exposed core would seem to allow. If the planet had been heated to the extreme temperatures necessary to blast away most of its mantle, why would such fairly volatile species remain? That contradiction forces the inquiry to broaden. If not entirely the product of a single blow, what alternative processes could produce the observed proportions? A quieter, more gradual explanation emerges from the physics of a young, irradiated disk. The protoplanetary disk is not a uniform slurry. It is threaded by gradients of temperature, pressure, and radiation, and it hosts forces that distinguish particles not only by size, but by composition. Photophoresis, the tendency for particles to be nudged by light as one side becomes hotter than the other, can separate silicate grains from dense metallic particles, preferentially migrating lighter, more volatile, rich dust outward and leaving iron-rich grains closer to the star. Magnetic interactions, aerodynamic drag, and the inward drift of pebbles under gas drag can further concentrate refractory material in the inner region. Pebble accretion, a process by which small, centimeter-to-meter scale solids are swept up efficiently by growing embryos, could have fed a growing Mercury with metal-rich pebbles, assembling a large core without the need for catastrophic later removal of mantle. In this picture, Mercury's anatomy is less the consequence of a single tragedy and more the natural consequence of initial conditions and transport processes in a particularly harsh inner zone of the disk. There is another chemical twist to consider: redox state. In environments where oxygen availability is limited, where the nebular gas is relatively reducing, iron will prefer to remain metallic rather than oxidize and bind into silicate minerals. A planet building from such a reservoir will naturally be iron-rich, a born-heavy world rather than a strict one. This mechanism dovetails with the volatile paradox. If the feeding zone had peculiar chemistry, the presence of sulfur and other volatile-bearing phases might be understandable without invoking post-formation heating, sufficient to remove them. A further possibility complicates the binary of single impact versus birth environment: multiple, incremental erosive collisions. Rather than one cataclysm, Mercury might have suffered a sequence of smaller erosive events, hit-and-run collisions, and repeated grazes that, gradually, removed mantle material. Each encounter would strip a little more until a disproportionately massive core remained. This hypothesis preserves the possibility of volatile retention, because intermittent contact and exposure might not have heated the body to the same integrated extremes as a single global melting event. No single explanation enjoys uncontested dominance. Each is supported by models and constrained by data in different ways. Discriminating among them requires multiple lines of evidence, precise isotopic ratios that could fingerprint source reservoirs, high-resolution mapping of crustal composition, a refined understanding of the interior state that controls magnetic dynamo behavior, and better constraints on the timing of Mercury's formation relative to the migration of gas giants in the system. Missions like MESSENGER have already reshaped the conversation. Successors, the instruments they carry, and the observations they return will refine the margins of plausibility. The presence of a magnetic field complicates and enriches the narrative. Mercury's global magnetism, weaker than Earth's, but unequivocally present, suggests an active or formerly active dynamo in a partially molten metallic interior. How does a small planet, supposedly cooled and contracted, maintain such activity? Some models invoke a combination of slow cooling, compositional convection driven by the crystallization of an inner core that expels lighter elements into an outer, convecting shell, and tidal interactions or latent heat release. The dynamo's history is itself a deep time chronicle. It may record the thermal evolution, the timing of core crystallization, and the rates of heat loss that together determine whether the planet retained enough internal vigor to sustain a magnetic field as it aged. A magnetic record, in short, is a thermodynamic fossil. The physical features of Mercury also read like a ledger of change. The lobate scarps, cliff faces that can stretch for hundreds of kilometers, indicate that the planet has shrunk as it cooled by, an amount sufficient to produce global compressional strains. The hollows, newly discovered and pristine in appearance, hint at ongoing loss of some volatile component, perhaps bound sulfur-bearing compounds that sublimate under intense solar heating or are removed by sputtering. These surface processes are not merely cosmetic, they reveal the interplay between interior chemistry and surface environment, between the deep memory held in the core and the ephemeral exosphere blown by the sun. All of this observation rests upon the limits of seeing. Mercury's proximity to the sun makes it a difficult target from Earth, and from space, glare, thermal management, and orbital energetics conspire to render missions expensive and infrequent. The dataset is therefore precious. Each new image, spectrum, and gravity measurement tightens the net of inference around those multiple origin scenarios. The effort to understand Mercury is itself an exercise in patient accumulation, a slow reading of marginalia. In the broader philosophical frame adopted by the earlier meditations on planetary palimpsests, Mercury is instructive. It shows how a small world, ostensibly simple, can encode a plurality of histories. The proportions of metal to silicate challenge the assumption that planetary identity is set in a single stroke. They force recognition that both primordial sorting and violent remodeling are plausible, and that the truth may be braided from both. Mercury insists that planets are not monolithic answers, but fragments of a conversation between chemistry, dynamics, and time. For the human observer, there is a humbling cadence to this realization. The question of why Mercury's core occupies so large a share of its volume is also a question about contingency, about what chapters of the early solar system were written in ink and what were erased or edited. Mercury's existence underscores the fragility of planetary narratives, the ease with which an entire mantle can be redistributed, the sensitivity of outcomes to gradients in a disk, the capacity of tiny forces on small particles to reorder matter on planetary scales. It reframes the reader's place in the cosmos, not as the architect of a deterministic story, but as an interpreter of marginal notes left by capricious processes. Ultimately, the inquiry into Mercury is emblematic of the larger project, to read planetary records with an imagination tempered by method. The planet's large core is not just an isolated oddity, it is a test case for theories of accretion, for the physics of disks, for the chemistry of early solar reservoirs, and for the dynamical violence of late-stage collisions. Each plausible mechanism carries implications, and each implication radiates outward, affecting how one comprehends inner system architecture, exoplanet demographics, and the range of planetary outcomes that nature permits. The current answer is therefore not a closing statement, but an invitation. Mercury offers puzzles that are soluble only by a patient conversation between observation and theory. It asks for more precise isotopic measurements, for tighter constraints on interior structure, for high-fidelity models of particle sorting in luminous disks, and for the courage to accept multi-causal explanations. The planet, like a stubborn marginal note in a great book, resists being summarized with a single line. It insists that the reader linger, compare passages, and allow multiple plausible histories to coexist until evidence chooses. And so the small, scorched world nearest the sun remains an emphatic reminder of planetary humility. Its days are blistering, its nights are frigid, its exosphere is ephemeral, its surface writes and erases. Its heavy core is an insoluble-sounding contradiction that, with patience, invites an expanding circle of questions rather than a definitive closure. In the slow grammar of deep time, Mercury's disproportionate heart is a punctuation that provokes rereading. It makes the listener keep turning pages, attentive to marginal clues that might finally reveal whether this dense planet is the result of violent reworking, subtle sorting, a reductive chemistry, or a braided mixture of all three. What would happen if two nearly identical siblings were separated at birth and raised under different suns? Imagine a pair of worlds born of the same dust, similar in mass, similar in radius, starting their lives with comparable inventories of rock and volatile. One remains cool enough, lubricated by oceans and plate tectonics, to host an evolving biosphere. The other, for reasons that are maddeningly subtle and variously argued, walks a different trajectory, toward an atmosphere so thick and unyielding that the surface is broiled to a temperature where lead would liquefy. This sibling pair is Earth and Venus. Their resemblance is intimate, their contrast is a lesson in contingency writ large. At first glance, Venus is almost mockingly ordinary. Its diameter is within a few percent of Earth's. If the two planets were twins in a photograph, size would not betray them. But the likeness ends there. Venus wears an atmosphere 90 times the pressure of Earth's, a deep, crushing column of mostly carbon dioxide, cloaked in thick clouds of sulfuric acid that reflect and scatter sunlight. The surface temperature hovers around 460–400 degrees Celsius, an oven sustained not simply by proximity to the sun, but by the atmosphere's capacity to trap heat. Where Earth's greenhouse effect is a moderate blanket, Venus's is an intolerable furnace. The planet is a household warning label framed on a cosmic scale. Small differences in boundary conditions, compounded over deep time, can produce planetary fates that could not be more opposed. The central puzzle is not merely descriptive, it is causal. Venus's present state is well described, but what produced the runaway greenhouse that transformed a potentially temperate world into a searing one? Multiple mechanisms compete for explanatory power, and the truth likely weaves them together. The narrative must begin with the simplest distinction: water. Water is a planetary thermostat and a chemical scavenger. On Earth, rain drives the carbonate-silicate cycle, a slow but relentless process that removes atmospheric carbon dioxide by weathering rocks, transporting carbonates to the oceans, and ultimately subducting carbon-rich sediments into the mantle through plate tectonics. Over millions of years, this geochemical servo stabilizes climate. Greenhouse gas accumulations are checked because warmer temperatures accelerate weathering, which in turn draws down CO2 and cools the planet. But this thermostat depends on liquid water and active crustal recycling. Remove the ocean, and the mechanism fails. One plausible class of explanations for Venus's fate invokes early loss of water. In the young solar system, the sun was dimmer, but Venus received more insolation than Earth simply by being closer. If Venus began with a significant inventory of water, rising temperatures could have driven a moist greenhouse, water vapor, a powerful greenhouse gas, would have increased the lower atmosphere's opacity. As temperatures rose, evaporation would accelerate, injecting even more water vapor into the stratosphere where ultraviolet photons from the sun could break H2O molecules apart. Freed hydrogen, light enough to escape the planet's gravity, would stream away to space. Over millions to hundreds of millions of years, our planet could shed its oceans by this photodissociation and hydrogen escape process. The elevated ratio of deuterium to hydrogen in Venus's atmosphere, a heavy isotope enrichment suggesting preferential loss of lighter hydrogen, supports the idea that Venus once possessed more water than it currently displays in its atmosphere. But water loss is not simply a tale of evaporation and escape. It is entangled with planetary geology and atmospheric chemistry. Without oceans to enable weathering, carbon dioxide emitted by early volcanic activity cannot be sequestered into carbonates at scale. Instead, it accumulates in the atmosphere. Radiative balance shifts, and a self-reinforcing loop feeds on itself. More CO2 produces higher surface temperatures, which promotes further degassing and prevents any transient condensation of water back into stable reservoirs. Over deep time, outgassing and failure to sequester carbon lock a planet into a high CO2 state. Yet this explanation leaves open crucial uncertainties. When did Venus lose its water? Was the process early and rapid, occurring within the first few 100 million years? Or was there a protracted, more complex history where oceans lingered for 1 billion years before vaporizing? Geological evidence from Venus is maddeningly sparse. The planet's surface displays a relatively young age statistically. A paucity of impact craters implies widespread resurfacing events in the geologic past that buried older terrains. If a global volcanic resurfacing occurred, it could have erased the most telling signatures of any ancient oceans, a palimpsest overwritten by flows and mantling materials. Thus, the memory of potential habitability might be sealed under thousands of kilometers of basaltic flows and tectonic scars. Volcanism itself is a double-edged actor in the Venus story. Massive or sustained volcanic outgassing supplies CO2, sulfur compounds, and water volatile inventories crucial to atmospheric development. It can also lift particulates and aerosols into the atmosphere, producing short-term cooling by reflecting sunlight. But on Venus, sulfur chemistry has become a permanent atmospheric act. Sulfur dioxide and other sulfur-bearing gases react to produce dense clouds of sulfuric acid, which sit at altitudes that make the planet highly reflective. Venus's albedo is among the highest of any planet. Paradoxically, those same sulfuric clouds, while reflecting some incoming sunlight, sit above a troposphere so dense that infrared energy from the surface is trapped, maintaining the greenhouse. The atmospheric superrotation, where the upper atmosphere circles the planet far faster than the planet itself rotates, redistributes heat and helps maintain global thermal structure, but it does nothing to ameliorate the fundamental imbalance of radiative forcing created by an atmosphere heavy with CO2. Planetary magnetic fields and rotation rates add further complexity. Earth's magnetic dynamo helps shield the atmosphere from the solar wind, partially mitigating atmospheric erosion. Venus, by contrast, lacks a significant intrinsic magnetic field. Some of that absence may stem from its slow, retrograde rotation and differences in internal heat flow. The details of the core's convective state are not fully known. The weak magnetic protection might have facilitated the gradual escape of atmospheric constituents, especially light hydrogen. But the bulk removal of heavier gases by this route is unlikely. The interplay of rotation, internal cooling, and magnetic shielding is a complicated three-way conversation that shapes a planet's vulnerability to external drivers. The story also touches a faint young sun paradox. The early sun was dimmer, yet planets near it experienced different thermal fates. Slight differences in initial volatile inventories, in early solar activity, in the timing and magnitude of volcanic episodes, and in orbital and rotational evolution could nudge otherwise similar planets along dramatically different climatic trajectories. In some plausible scenarios, Venus, just a little closer to the source, tipped past a critical threshold where radiative physics and atmospheric chemistry conspired to make the greenhouse irreversible. On geological timescales, speculation runs further. Some models suggest that Venus might have had a habitable epoch, a period when surface temperatures permitted liquid water and, potentially, life. If life ever arose, its traces would be extraordinarily subtle or erased. The surface geology has been rejuvenated in ways that would bury and metamorphose organic residues, and the corrosive atmosphere would alter molecular signals. There is a more exotic conjecture. Life, if it ever existed on Venus, may have adapted to cloud layers where temperatures and pressures are less hostile. The middle cloud deck offers conditions that are comparatively temperate, with droplets and aerosols suspended in a chemically active environment. The idea that a planet's clouds could host microbial habitats is speculative, but it serves as a sobering reminder that habitability is not defined exclusively at the surface. Yet the chemical milieu there, dominated by concentrated sulfuric acid, is not congenial for known terrestrial biochemistry at scale. The evidence for and against such aerial life remains highly circumstantial and controversial. The measurement record provides constraints, but also puzzles. The isotopic fingerprints in the atmosphere, noble gas ratios, and the deuterium enrichment narrate a history of loss and alteration. Remote sensing reveals surface minerals that are difficult to reconcile with extreme heating and provide hints about the planet's volcanic and tectonic past. Observations of changing sulfur dioxide levels in the upper atmosphere suggest episodic volcanism, implying that Venus may still be geologically active. If true, ongoing volcanism would maintain atmospheric chemistry that supports the dense cloud cover and greenhouse state, but the lack of unambiguous seismic or crustal data leaves room for competing interpretations. Beyond deciphering Venus's past, the planet functions as a laboratory for understanding planetary habitability in general and for interpreting exoplanets. Many exoplanets discovered in close orbits around their stars, hot terrestrial candidates, might be Venus-like rather than Earth-like. The line between a temperate world and a hellish greenhouse is not a single distance from a star, but a function of atmospheric composition, geologic processes, initial volatile budgets, and stellar activity. The concept of a habitable zone must be refined to account for these interdependencies. A planet in the traditional habitable band might still become inhospitable if its atmospheric evolution runs away in the wrong direction. The ethical and philosophical resonance of Venus as a mirror for Earth is unavoidable. Observing a world so like our own that it is almost a doppelganger, and then seeing how easily it can end up inhospitable, evokes a mixture of awe and unease. It forces a recognition of fragility, Planetary climates are not foreordained to be benign. Feedbacks can amplify small perturbations into irreversible shifts over geological timescales. To listen to Venus is to accept a cautionary tale about inertia, cycles, and thresholds. It invites a sober humility in the face of planetary stewardship. Scientific curiosity is active and methodical in response. The last decades of orbital missions, from Magellan's radar maps to Venus Express and Akatsuki's atmospheric eyes, have sketched the planet's outline. In the near future, missions planned with goals to probe surface composition, noble gas inventories, and atmospheric structure, missions like Davinci Plus and Veritas among them, promise to tighten constraints. These missions aim to read the planet's text more carefully, to measure isotopic ratios that could timestamp water loss, to image tesserae and highland terrains that may preserve older crustal histories, and to sense surface compositions that could betray past oceans or present volcanism. Each piece of data is marginalia, a smudge in a palimpsest that, when combined, can tilt interpretations away from speculation to plausible chronology. Yet even with improved observations, caution is required. Geologic and atmospheric processes interact on timescales that are long and nonlinear. Explanations that emphasize a single trigger are seldom sufficient. A synthesis must accept that episodes of volcanism, photochemical water loss, the absence of a functioning carbonate, silicate thermostat, variations in stellar irradiation, and the timing of shield-like magnetic protection all contribute. The result is not a single canonical story, but a web of contingent pathways. Venus teaches that planetary histories are braided, and that causation on deep time scales is frequently multifactorial. Finally, the image that lingers is not one of definitive closure, but of invitation. Venus is a mirror that refuses an easy reflection. It is a patient skeptic of anthropocentric narrative where the mind seeks a single origin story. The planet offers complexities. For Earth, the study of Venus is not merely academic. It is a reminder that long-term habitability is neither inevitable nor static. The thin line between hospitable and hostile climates is traced by myriad processes that act over eons. Understanding Venus is therefore a project of modesty as much as of science. It teaches what could be lost, what must be measured, and what questions to ask of other worlds. To read Venus's long runaway page is to learn how fragile a planetary biography can be, and to carry that lesson forward, not as prophecy, but as counsel. What if the true secret of a world's ability to harbor life is not a single ingredient, but a pattern of motion, a planet that knows how to breathe? That image of a world inhaling and exhaling heat, chemicals, and water frames a different question than the usual inventory of rocks and gases. Plate tectonics and oceans are part of that respiration, but are they the deciding elements, or merely components in a larger choreography? To approach that question, one must turn to Mars, the Red Promise, a planet that once seemed to offer an answer and now insists on a more complicated one. Mars arrives in the story as a ledger of promises made and partially kept. From orbit, the planet presents itself as a cold, rust-stained sphere, but its pages contain handwriting from an earlier time. Valley networks that branch like dried river deltas, layered sediments that read like lakebed diaries, minerals that form in the presence of water. The visible geology tells of a youth when liquid water flowed across the surface, carving valleys and pooling in basins. Clay minerals, phyllosilicates, and certain iron and sulfur compounds speak of neutral to mildly alkaline waters, environments that on Earth would be considered friendly to life. In a quiet geological shorthand, Mars once had the ingredients that elsewhere are associated with habitability. The evidence is precise in tone but ambiguous in narrative. Valley networks radiate from highlands and converge into basins. Some are dendritic, implying sustained precipitation or runoff rather than a single catastrophic flood. Delta-like deposits appear within crater basins, their braided layers reminiscent of fluvial systems on a wetter Earth. Elsewhere, layered sulfate-rich deposits evoke evaporation and desiccation, hints of episodic lakes or seas shrinking under an arid sky. The story these features tell is not of a planet uniformly warm and wet, but of epochs and locales where water persisted long enough to leave chemical and morphological marks. The Noachian period, more than 3 billion years ago, emerges as a window, perhaps a series of windows, when surface conditions could have supported aqueous chemistry at the scale of rivers, lakes, and shallow seas. Yet the promise carries a paradox. Mars's ancient hydrology seems to end in a prologue. For reasons that are the focus of intense scientific scrutiny, The planet's surface water largely disappeared or retreated to cold traps and subsurface reservoirs. The contemporary Martian surface is dominated by permafrost, polar caps of water and dry ice, and regolith baked by thin air and weak insulation. Where oceans might once have lapped, there are now broad plains and fractured basins. The transition from a potentially habitable Noachian to an arid Hesperian and Amazonian involves multiple actors: atmospheric thinning, loss of heat, volcanic episodes, impacts, and orbital variations in obliquity. At the heart of the transformation sits a central mechanism: atmospheric escape. Mars is smaller and less massive than Earth, and its gravity holds atmospheric particles less tightly. Early in its history, Mars likely possessed a thicker atmosphere, perhaps buoyed by volcanic outgassing and by a greater abundance of water. But the planet's magnetic shield, a protective dynamo generated in a convecting metallic core, appears to have shut down early. Without a global magnetic field, the solar wind could directly strip upper atmosphere particles away. Measurements from recent missions have traced ions being peeled off by the solar wind and inferred long-term loss rates of carbon and water. Ultraviolet photons break apart water molecules in the upper atmosphere. Lighter hydrogen escapes to space, leaving heavier deuterium preferentially behind, a chemical footprint that Mars scientists read as evidence of significant past water loss. But escape is not merely a function of size and magnetism. The red planet's fate involved the dance between internal heat and surface processes. Active plate tectonics on Earth is one of the most efficient ways to circulate carbon between the atmosphere and the deep interior. On Mars, such recycling, if it ever occurred at large scale, apparently ceased early. The absence of long-lived global plate tectonics would limit the sequestration of atmospheric CO2 into carbonate rocks and the return of volatiles from the mantle in a controlled fashion. Instead, volcanic activity on Mars appears to have been more episodic and concentrated in enormous provinces, such as Tharsis, a volcanic bulwark that rearranged the planet's surface and perhaps altered atmospheric dynamics through massive outgassing. Those episodic pulses of volcanic vigor may have prolonged habitable conditions locally or temporarily, but they could not deliver the same steady global regulation that plate tectonics affords. This contrast between a planet's ability to cycle chemical species and its capacity to hold onto an atmosphere crystallizes the broader question: which planetary trait is decisive? The presence of oceans, the presence of tectonics, the size and gravity, the magnetic field, or the initial volatile endowment? Mars demonstrates that none of these factors acts alone. Habitability seems to require a confluence, sufficient inventory of volatiles, a mechanism for long-term retention of atmosphere, an energy flow that creates and sustains chemical disequilibria, and environmental stability at the scales required for complex chemistry to develop. It is the pattern of exchange, the breathing, that matters. The coupling of atmosphere and hydrosphere with the solid planet and with external energy sources. The search for life on Mars therefore shifts focus from a simple checklist to a search for sustained disequilibrium. Life, as a physicist might say, exploits gradients. Wherever there is a flux, redox gradients at the interface of oxidized and reduced minerals, thermal gradients around hydrothermal systems, chemical gradients where sulfate meets organic carbon, there is potential for metabolic activity. On early Mars, environments capable of generating such gradients existed. Hydrothermal systems associated with volcanic provinces could have hosted warm, mineral-rich fluids. Shallow lakes and ephemeral springs could have concentrated reactants. Subsurface aquifers, insulated from the harsh surface, could have provided stable temperatures and protection from radiation. This last possibility, life beneath the surface, looms large in Martian speculation. The ancient surface may have been hospitable only intermittently or locally, but the subsurface offers a form of planetary refuge. Buried pockets of water, porous rocks saturated with brines, and fractures permeated by circulating fluids could harbor niches where chemical energy is available and where conditions change slowly. In the deep past, such niches would have been more numerous and perhaps connected. Today, they might be relics. Pockets of habitability isolated by the planet's long cooling and desiccation. To read Mars's habitability, one must therefore think not only in surface terms but in 3 dimensions, a stratified world where the subsurface stores both water and memory. The search for biosignatures on Mars is, in consequence, an exercise in forensic patience. Organic molecules are being detected in ancient mudstones in Gale crater by rover instruments, but interpretation is cautious. Organics can form abiotically and can survive in altered forms indistinguishable from biological remnants without detailed contextual clues. Methane spikes in the atmosphere, intermittent plumes observed by orbiters and rovers, add an evocative hint of active chemistry, perhaps biological or perhaps geothermal. The seasonal variation of methane, coupled with spatial heterogeneity, points to localized sources or transient sinks. Yet an unequivocal attribution remains stubbornly out of reach. Methane can be produced by serpentinization, the water rock reaction that generates hydrogen and then methane, or by photochemistry acting on organics delivered by meteorites. Part of the difficulty lies in preservation. Mars is a planet of exposure. Ancient surfaces are often oxidized and irradiated, and the harsh ultraviolet and cosmic ray flux near the surface breaks down complex organics over geological timescales. The very processes that etched valleys and layered deposits also destroy potential biosignatures. That is why the discovery of finely laminated sedimentary rocks matters so profoundly. Muds laid down in low-energy lakes can entomb organics and protect them from radiation, preserving chemical and isotopic records of past environments. These are the pages of the Martian book that remain legible. But knowing where to look still depends on understanding the planetary breadth. If tectonic recycling is minimal, then the surface becomes a one-way archive. What is buried stays buried, and what is exposed receives relentless radiation, making it harder to preserve delicate signals. Conversely, on a planet where recycling lifts material from the depths to the surface, biosignatures may reappear, but also be reworked or destroyed. Each mechanism affects both the chance for life to develop and the likelihood that its traces will persist long enough to be found. Mars, in its red austerity, therefore functions as a counterfactual laboratory. It is an experiment in what happens when some of the Earth-like parameters falter. The planet had water and energy gradients. It had potential habitats. Yet its system-level behavior, weak retention of atmosphere, early cessation or lack of global tectonics, susceptibility to solar stripping, conspired to attenuate long-term surface habitability. The red promise remains only partially fulfilled. That incompleteness is instructive. Habitability over geological timescales is not merely about the instantaneous presence of liquid water, but about the mechanisms that maintain water and climate in a non-equilibrium state over millions and billions of years. The lesson extends beyond Mars. When imagining worlds elsewhere, it becomes insufficient to place them in a habitable zone by distance alone. A planet's capacity to breathe, to circulate materials between surface and interior, to sustain a magnetic shield long enough to retain an atmosphere, to host steady energy flows that create reducible gradients, may be more determinative than any single constituent. Exoplanets found in temperate orbits must therefore be evaluated for their geodynamic vigor, for signs of atmospheric stability, for histories that allow persistent chemistry. Even in the case of Earth, the interplay of mantle convection and surface water, of life and rock, has produced a unique feedback loop that stabilizes climate and recycles nutrients. It is a planetary respiration that extends across eons. There is a melancholic beauty in Mars's story as well. The planet is not a failure, it is a revelation. Its ancient rivers and lakes remind the observer that habitable conditions can arise in unexpected places. Its subsequent decline underscores fragility and contingency. For anyone who listens closely, Mars speaks not only of possibilities lost, but of processes that must be conserved if a world is to remain a cradle for complexity. The red promise is therefore both invitation and admonition. It invites exploration of subsurface refugia, careful analysis of ambiguous chemical clues, and humility in assigning cause. It admonishes against assuming permanence on the basis of transient conditions. The present-day exploration program reads Martian marginalia with instruments rather than imagination, orbiters that map mineralogy and subsurface structure, rovers that analyze sedimentary layers and organics, landers that probe interregolith and measure atmospheric escape. Sample return campaigns aim to close the loop, to bring Martian sediments into Earth laboratories where isotopes and molecular structures can be parsed with greater sensitivity. Each instrument peels back another layer of uncertainty. Each finding either strengthens the case for a once hospitable Mars or complicates it with new anomalies. Ultimately, the decisive element for life's emergence and persistence may not be traceable to a single chemical or a single process. A planet that breathes, that couples its atmosphere to its hydrosphere and interior in a sustained, regulated rhythm, creates the conditions where chemistry can flower into biology and where biology, once present, can feed back on planetary scale. Mars shows what happens when that breathing falters, windows of promise close, refuges shrink, and the record left behind becomes fragmentary. The red promise is therefore an argument for system thinking and planetary habitability, a reminder that life is less a product of static inventories and more a consequence of long-term, interconnected processes that keep a world alive at the scale of deep time. In the end, the question is posed as a provocation rather than a resolved claim. What does it mean for a planet to breathe? To answer that, the reader is asked to look not at lists of required elements, but at rhythms, the rise and fall of atmospheres, the cycling of carbon, the slow choreography of water between sky and ground, the interior convulsions that return elements to the surface. Mars, with its red promise and its silent cautions, remains one of the most eloquent chapters in that unfolding inquiry. The planet's pages are not fully read. They are stitched with water-scarred sediments, magnetic signatures, and the faint traces of chemistry that may or may not have once hosted life. To follow them is to accept that habitability is a verb, an ongoing process, and that discovering which planets truly know how. To breathe will require patience, instruments, and a humility before time that grew in the earlier pages of the book. What does it mean to find the faint channel of a river where no water now flows, a dark, braided scar across an otherwise silent plain? And what might be secreted beneath frozen ground, tracked in a lattice of ice for millions of years, like ink preserved in an ancient, unreadable margin? These images, dried riverbeds and buried ice, are not merely topographic curiosities. They are invitations to a question as old and audacious as planetary science itself. Could microscopic life have taken refuge in these hidden places? And could those long, quiet refuges still whisper of a biology that once was? The first image is everywhere the listener has looked. Sinuous valley networks on Mars, meandering paleochannels cut into sedimentary plains, deltaic lobes tucked in crater basins. From orbit, they appear like fossil rivers, their sinuosity betraying a fluidity once present. These forms speak in morphological dialects that terrestrial geomorphologists understand well. On Earth, such patterns form from sustained surface flow, rainfall-fed rivers, ephemeral but repeated floods, groundwater sapping across permeable strata. On Mars, the scale and branching of many networks suggest persistence rather than a single catastrophic pulse. The valleys seem to read as if written by seasons, perhaps a string of rainy years, or by a climate that, for a period measured not in human generations but in geologic epochs, allowed liquid water to wander the surface. The second image is more covert, ice caskets entombed beneath regolith and dust, a subterranean memory that avoids the violent erasures of surface exposure. Radar profiles have revealed these reservoirs with an almost forensic clarity. Instruments like Sherrod and Marsis have returned subsurface echoes consistent with extensive ice sheets buried under sediments in mid-latitude provinces. Landers and rovers, the Phoenix mission, for example, have physically encountered ice within a meter or two of the surface. The spectrometer signatures and direct images of sublimation reveal that ice remains, sometimes only temporarily covered, sometimes capped by a desiccated armor. In permanently shadowed lunar craters and in the cold traps of Mercury, similarly secreted ices persist, captured in thermodynamic prisons where sunlight never reaches. Together, ancient rivers and buried ice define two modes of preservation and two potential theaters for life. Rivers, while active, rearrange and refresh landscapes. They create habitats rich and dissolved in suspended chemistry, energetic gradients, and fine sediments that can entomb organics. If microbial ecosystems ever thrived on a planet's surface, fluvial systems are a plausible place for both activity and preservation or burial. Buried ice, conversely, offers a different kind of longevity. Ice can cryogenically suspend organic molecules and microbial cells, slowing chemical degradation and shielding from radiation. In Earth's permafrost and in Antarctic subglacial lakes, life has persisted in deep time, metabolizing slowly at the thermodynamic margin or waiting in stasis until circumstances improve. These terrestrial lessons fuel the hypothesis that buried ice on other worlds could have been a sanctuary, but preservation is only half the story. The question of whether life could have arisen in these settings, or whether it could have survived there long enough to be detectable today, rests on energy and chemistry. Life, as understood by terrestrial biochemistry, requires not only water but a continuous supply of usable energy and a means to obtain nutrients. Where sunlight disappears beneath ice or where surface conditions become too hostile, alternate energy sources must be available. Radiolysis of water by natural radioactive decay can split H2O into molecular hydrogen and oxidants, creating redox pairs that microbes can exploit. Serpentinization, the reaction of ultramafic rock with water, can produce hydrogen and methane abiotically, offering another continuous energy supply. Hydrothermal systems at the interface of hot rock and liquid water combine chemical and thermal gradients, creating niches rich in disequilibrium. On icy moons, these ideas are not hypothetical. The plumes erupted from Enceladus, and the induced magnetic signals around Europa point toward subsurface oceans interacting with rocky interiors. There, hydrothermal chemistry could supply the same energy fluxes that, on Earth, are known to host complex microbial communities. Mars, however, presents a layered argument. Valley networks and sedimentary deposits offer morphological and mineralogical evidence of long-lived water, at least episodically. Clay minerals and certain sulfates are fingerprints of aqueous geochemistry, but the persistence of water on the surface requires atmospheric pressure and temperature conditions that Mars appears to have lost. In the absence of a thick atmosphere and pervasive surface water, the subsurface becomes the refuge of interest. Porous rocks, buried aquifers, and ice-rich permafrost can host brines where salts depress the freezing point, allowing liquid films or pockets to exist even at sub-freezing temperatures. Perchlorates, salts discovered in Martian regolith, are hygroscopic and can form eutectic liquids when combined with water vapor, providing transient but potentially recurrent habitats. In addition, geothermal gradients and episodic volcanic heating could produce localized melting or the recharge of groundwater systems. Detection strategies therefore divide into two types: remote reconnaissance and direct sampling. Remote sensing can map paleochannels, identify clay-rich sediments, and determine the distribution and thickness of buried ice via radar. It can also infer subsurface structure through gravity anomalies and thermal mapping. But only direct, context-rich samples can reveal molecular biomarkers, long-chain organic molecules, isotopic fractionation suggestive of biological metabolic pathways, cellular microstructures preserved in fine-grained sediments. Yet drilling into icy or sedimentary deposits is technically challenging and ethically fraught. Planetary protection protocols demand that any attempt to retrieve putative biosignatures avoid forward contamination. A terrestrial organism introduced into a cryopreserved niche could snowball the very question being asked. Thus, the design of a mission must marry engineering, cleanliness, and care, sterile drills that can reach meters into permafrost, sample caches that remain sealed until analyzed in the most controlled laboratories available. Beyond the technical and ethical constraints lies interpretive caution. Organic molecules are not, by themselves, proof of biology. Abiotic synthetic pathways can yield a suite of organics, and post-depositional alteration can produce patterns that mimic biological fractionation. The statistical and isotopic context, ratios of carbon, nitrogen, and sulfur isotopes, molecular complexity metrics, chirality, must be read alongside sedimentology and mineralogy. A fossilized cell or a pattern of sedimentary microstructures that match known biological morphologies would be more persuasive, but such finds are rare and demanding to extract convincingly. The listener is left with an emotional ambivalence, hope braided with restraint. The image of a microbe whispering in ice seems romantic, and yet the scientific method insists on skepticism. The archive is partial, the page edges frayed, and the margin notes ambiguous. This is precisely where the thrill of deep-time inquiry lies, in the patient task of decoding faint signals. From these near and buried dramas, the narrative leaps outward and upward to the largest presence in the sky, a gas giant that does not merely orbit but dominates. Jupiter, proud in its bulk and dynamism, is a different kind of palimpsest. It writes quickly and loudly, its handwriting composed of bands, belts, and storms that churn with energy unseen on rocky worlds. To think about Jupiter is to reckon with scale. The planet's mass is more than twice that of all other planets combined, and with that mass comes a capacity to shape the architecture of the entire system. At the heart of Jupiter's influence is its magnetic field, a magnetosphere so vast it would swallow the sun's diameter several times over. The origin of this behemoth field is the physics of extreme interiors. Under the enormous pressure and heat of Jupiter's deep layers, hydrogen becomes metallic, a fluid conductor that, set into motion by the planet's rapid rotation, drives a powerful dynamo. The result is a magnetic engine that accelerates charged particles into radiation belts, scours the surfaces of nearby moons, and scythes the solar wind into a complex bow shock and magnetotail. Observationally, this magnetosphere is not abstract. It is manifest in auroral emissions at the poles, in the radial hiss that betrays trapped particles, and in the currents that thread the system. The magnetosphere does more than produce spectacle. It interacts with moons in dramatically consequential ways. Io, the innermost of the large moons, is volcanically hyperactive, shedding sulfur and sodium that become ionized and caught in Jupiter's magnetic embrace, forming a plasma torus that feeds energy back into the system. Europa, by contrast, bears an induced magnetic signature, a subtle but telling oscillation measured by spacecraft passing through the Jovian field. This induction is best explained by a conducting layer beneath Europa's icy shell, a saline ocean. The implication is profound. The magnetic field becomes not merely a planetary curiosity, but a diagnostic tool, revealing subsurface oceans that might host the chemical gradients and energy flows necessary for life. Jupiter's atmosphere, meanwhile, reads like a weather book on steroids. Bands of zonal wind shear delineate the planet into belts and zones, each with different colors and convective dynamics. Embedded in this zonal tapestry is the Great Red Spot, an anticyclonic storm whose diameter once exceeded that of Earth and whose persistence for centuries challenges models of vortex decay. The spot is a study in longevity and entropy. It resists shear, absorbs smaller storms, and sometimes appears to shrink or change hue, hinting at processes deep within the atmosphere or compositional shifts. Recent probes and Jovian explorers have revealed that atmospheric phenomena on Jupiter penetrate far deeper than the upper cloud decks, that ammonia and water are distributed in complex patches, and that the planet's deep circulation carries momentum and heat into the interior in ways only now being mapped by gravity sensing and microwave instruments. Jupiter's role in the larger story of the solar system is equally ambivalent. It is simultaneously a protector and a provocateur. Its gravity can deflect long-period comets, reducing the impact flux in the inner system, yet the same gravitational reach can fling objects inward, perturbing trajectories and delivering volatile, rich bodies to terrestrial planets. Models of early migration, scenarios like the so-called Grand Tack, suggest that Jupiter's early movements inward and then outward may have sculpted the inner solar system, influencing the mass distribution and the volatile endowment of Earth and its neighbors. In other words, Jupiter's deep-time choreography helped determine not only its own fate, but also the conditions for habitability nearer the Sun. The listener faces a paradox that repeats across scale. Where an ancient river and a buried ice deposit can be read as possible sanctuaries for microbial life, Jupiter insists on a different kind of influence. Its magnetic field can be diagnostic of subsurface oceans, its storms are laboratories of fluid dynamics at planetary scales, and its gravitational history is written into the orbital architecture of the entire system. The same planet that perhaps shielded early Earth from a higher flux of catastrophic impacts also contributed to a delivery system of volatiles and organics. The scale of influence begets humility. In deep time, no planetary story is isolated. The two threads, paleochannels and ice, and the grand dynamics of Jupiter, meet again when considering habitability beyond Earth. Subsurface oceans hinted at by Jupiter's magnetic signature or inferred from icy moon plumes are places where the logic of buried water and preserved chemistry apply on a planetary scale. If Europa's shell houses a warm, saline ocean sculpted by tidal heating and fed by rocky seafloor interactions, then the same energetic recipes that could preserve biosignatures in buried ice hold there too, magnified by volume and fed by a different energy source, gravitational flexing rather than sunlight. Likewise, Enceladus's plumes have already afforded the rare opportunity to sample material ejected from deep within an icy world, bypassing the need to drill. These samples, sticky with organics and perhaps with the chemical products of hydrothermal chemistry, are the modern equivalent of reading a palimpsest's marginalia that someone has chosen to reveal. The compelling quality of these inquiries is not merely scientific. There is a moral tone to the patient search, to accept that answers, if they come, will often be partial, contested, and slow. The planetary book is a palimpsest not only of geology and chemistry, but of human curiosity and restraint. Each radar echo, each spectral line, each gravity anomaly is a marginal note to be read carefully, cross-checked, and placed within a broader web of inference. In that web, ancient rivers and subsurface ice are not isolated mysteries. They are connected to the grand dynamics of gas giants, to the tidal warmth of moons, and to the deep time processes that dictate whether a world preserves or erases the traces of its own life. The question that remains, recirculating in the listener's mind, returns to the first image. If microscopic life once existed in a buried river delta or in a frozen aquifer, would the signature of that life survive the grammar of geological time? And if it did, will instruments and patience be enough to read it? The adjacent question asks whether the behemoths of the solar system, with their magnetic fields and storms, are collaborators in preservation or agents of change. Both questions resist simple closure. They are the marrow of the long inquiry. They demand measurements that are precise, missions that are careful, and an imagination willing to entertain smallness, temporariness, and the persistence of mystery in equal measure. Exploration advances in fits and patient increments. Radar maps grow denser. Landers and rovers test chemistry with increasingly sensitive kits. Orbiters decouple magnetic whispers into structural truths. Proposals for cryogenic drills and plume. Fly-through samplers press forward. Each technical advance is a new lens for old questions. The faint channels etched in dust, the ice that hides in permanent shadow, and the giant neighbor whose magnetism exposes hidden seas. Together they make a narrative that is less a finished chronicle than an unfolding inquiry, an extended meditation on continuity, and erasure, on protection and perturbation, and on the slender possibility that the planet's long book still contains a readable line about life beneath its frozen margins. What does it mean to stand beneath a sky whose storms are larger than continents, and then to ask, with a kind of vertiginous curiosity, what lies beneath those rolling clouds? The image is almost obscene in its scale. Bands of wind so broad they could swallow hemispheres, vortices that last for generations, a planet whose visible features are themselves the margins of a deeper, hidden story. Saturn, with its languid rings and its roiling, banded face, invites a deceptively simple and profoundly difficult question. Inside that immense, thick envelope of hydrogen and helium, is there a compact, solid heart, a true core of rock and metal, or is there instead a vast, supercritical ocean, a seamless transition from gas to a fluid so dense that the language of surfaces and layers begins to betray its adequacy? The question is not metaphysical. It is physical, tied to pressures that are almost incomprehensible and to matter pushed to states the Earth has never seen. Under the glare of the sun, Saturn plays a theatrical role. It is a pale golden lantern, its rings a glittering diadem. But the planet's external theatrics are only punctuation. The deeper text speaks of phase transitions and gradients, of hydrogen compressed to the point where it becomes metallic and conducts electricity like a metal, where helium droplets might rain out from a cooling interior, and where heavy elements could be smeared into the envelope rather than locked into a neat central lump. To read that text, scientists have listened to the planet in every way they can. Gravity, magnetic fields, and the seismology of ring waves are the instruments of interrogation. A planet's gravity field, the tiny perturbations it exerts on a passing probe, encodes the distribution of mass within. Cassini's daring final orbits, plunging between the rings and the planet itself, gathered exquisitely precise gravity data that have rewritten the speculative maps of Saturn's interior. The data hint at something unexpected rather than a compact, well-defined core. Saturn may harbor what is often called a diluted or fuzzy core, a central region where heavy elements taper off gradually into the surrounding metallic hydrogen. The boundary, if it exists, is not sharp. It may be smeared across a large fraction of the planet's radius. This possibility is alluring and unsettling in equal measure. A diffuse interior resists the comforting metaphor of a planet as a nested set of onion-like shells. Instead, it suggests a world whose primordial assembly and subsequent evolution mixed materials in ways that leave a long-lived memory, an ancient accretion history recorded not in discrete layers, but in gentle compositional gradients. Such a structure changes how one understands the planet's thermal evolution, its magnetic dynamo, and the long-term interactions between core and envelope. If heavy elements are dissolved into the metallic hydrogen, they alter both conductivity and buoyancy, making the internal dynamics more complex and perhaps explaining peculiarities in Saturn's magnetic field, a field unusually symmetric between north and south, and in its thermal emission, beneath the clouds, the chemistry is as odd as the physics. Hydrogen, helium, mundane on Earth, become exotic under Saturn's pressures. At sufficient depth and pressure, hydrogen transitions into a metallic state, a sea of electrons free to move, conducting electricity. Between the visible cloud tops and any putative rocky core lies a regime where hydrogen behaves as a supercritical fluid, neither gas nor liquid in the familiar sense, but a continuous phase with properties of both. Supercritical hydrogen can transport heat and dissolve other materials, and it offers a medium in which heavy elements, water, rock, iron, can be dispersed rather than relegated to a discrete core. Thus the question, solid core or supercritical ocean, is not binary in any naive sense. It is an invitation to imagine matter in ways that strain terrestrial metaphors. There is an emotional cadence to this scientific uncertainty. It produces a kind of humility, a recognition that planetary identity is not a checklist but a spectrum. Saturn's low mean density, less than water, if one could find a bathtub large enough, was one of the earliest clues that this planet is mostly gas. Yet mostly allows for nuance, and those nuances are where meaning accumulates. The possibility of a fuzzy core makes Saturn a different kind of palimpsest. The planet's deep structure preserves the record of formation and mixing, while its outer atmosphere records more recent meteorological dramas. Each domain is a different time scale of memory. The outer clouds carry seasonal and episodic events. The deep interior holds the slow script of accretion and differentiation. The storms themselves are a form of text. Saturn produces weather on planetary scales, the periodic emergence of great white spots, the monstrous convective plumes that have circled the planet at intervals measured in decades, equatorial jets that reach speeds of hundreds of meters per second, and the famous hexagonal wave at the North Pole, a geometric marvel of fluid dynamics. These phenomena are not merely aesthetic. They are the visible tips of convective processes driven by internal heat escaping through an envelope that is highly stratified by composition and temperature. The storms are large not only in spatial extent but in temporal persistence. A storm on Saturn can be an ancient thing in human terms, a meteorological event that unfolds across generations, and that persistence lends a certain melancholic beauty. The planet's atmosphere remembers in ways the human world cannot. And yet, for all their venerable scale, those storms are ephemeral compared to the planet's internal memory. Weather changes, interiors evolve slowly. To stand, even imaginatively, beneath Saturn's raging bands is to feel small, temporary, and to recognize that the planet's longer narrative is written in energies and materials beyond immediate perception. The question of core versus continuum is therefore not only a scientific curiosity, it is an existential prompt. How does long-term memory get stored in a world whose visible features are transient? Saturn's interior suggests answers that do not simplify, but that enrich. Memory is dispersed, history is smeared, the past is present in gradients rather than in single monuments. If Saturn's internal architecture presses against metaphors, its rings press against another set of contrasts, brilliance and fragility. From a distance, the rings are a triumphal ornament. They are bright, sharply defined, and astonishing in their complexity. Yet their brilliance is a kind of theatrical illusion. Up close, the rings are less like monolithic bands and more like a vast, thin sheet of debris. Countless particles ranging in size from microscopic dust to house-sized boulders, each tracing its own orbit, colliding gently, and guided by the gravity of Saturn and its moons. The rings are a granular disk, a dynamic, ephemeral structure in constant reworking. This duality, shining beauty and structural frailty, is the ring's fundamental paradox. Spectroscopy and imaging show rings composed primarily of water ice, which explains their high reflectivity. But their mass and longevity are matters of active debate. Cassini's grand finale orbits measured the rate at which ring material is being lost to Saturn, the subtle rain of particles that spirals into the atmosphere under the influence of electromagnetic forces and micrometeoroid bombardment. The process is painstakingly slow on human timescales, but rapid on geological ones. The rings might be relatively young, perhaps only tens to hundreds of millions of years old, and they are steadily losing mass. The same instruments that revealed ring rain also measured ring mass and suggested that the rings may be less massive than previously thought. If rings are young, they are a recent flourish. If they are losing mass, they are transient. There is melancholy in this transience. The rings can be read as marginalia added to a much older book. For a brief epoch in cosmic deep time, Saturn bears a jewel that will one day fade. The human response to this is twofold: awe at witnessing something spectacular, and sadness at the realization that it is temporary, an exquisite instance of temporality writ large. That sadness is not merely sentimental, it is epistemic. Rings that evolve on comparatively short timescales tell us about recent events, collisions that disrupted moons, the capture and destruction of comets, the ongoing exchange between rings and moons. If the rings are a recent phenomenon, They are a record of late-stage dynamics in the Saturnian system, the fingerprints of a disruptive event, and the slow aftermath of debris grinding and orbital evolution. The rings are also laboratories for complexity. Within them are density waves, bending waves, and self-gravity wakes. There are propeller-shaped disturbances caused by embedded moonlets. There are sharp edges sculpted by resonances which shepherd moons. There are ephemeral spokes that appear and disappear with the seasons, likely driven by electrostatic levitation of dust. Each of these features encodes physical laws in miniature: collisions and cohesion, gravitational resonance, electromagnetic charging. The rings are thus not merely pretty, they are diagnostic. They allow scientists to study processes of accretion and disk dynamics on a scale and at a resolution unavailable elsewhere. The rings are a microcosm of planetary formation itself, a laboratory where the grain-scale physics that once built entire planets can be observed in real time. The relationship between rings and moons is intimate and reciprocal. Moons shepherd ring particles, carving gaps like the Cassini division. Moons can be fed by ring material. Conversely, moons can feed rings. Enceladus, in a dramatic example, feeds a tenuous E-ring with plumes of water vapor and ice, revealing how internal geology and surface phenomena can sustain a ring. This dynamical interplay is part of the Saturnian palimpsest. Moons and rings write and rewrite each other's stories. A moon disrupted by a collision can seed a ring. A ring's mass can accrete into new satellites under the right conditions. The system is not static, it breathes, albeit on long timescales. All of these considerations return, in the end, to the motif of reading. Saturn is a book with multiple scripts. Its cloud tops are a cursive of storms and banded winds. Its interior is a slow, blurred manuscript of gradients and metallic seas. Its rings are a recent, twisting marginalia that will not last forever. Each layer requires a different method of reading: radio and gravity for the deep interior, spectroscopy and imaging for the atmosphere, in situ sampling and long-duration monitoring for the rings. The process is patient and aggregate. No single observation yields closure. Instead, understanding accrues through many marginal notes, each refining the narrative. There is also a final, quiet, ethical note. Observing a bright but fading ring evokes a human response, not unlike viewing a ruin, a mixture of wonder and transience that invites stewardship of attention. The sciences that read Saturn's pages are themselves contingent cultural practices, small and temporary, but they can, with humility and perseverance, extract meaning from the slow grammar of the planet. To know Saturn is to accept that some answers will remain provisional, that the dichotomy of solid core versus supercritical ocean may dissolve into a more nuanced picture, and that the ring's beauty is not eternal, but precisely because of that, all the more worth seeing while it lasts. In that temporality lies a kind of consolation. If planets are palimpsests, and if their most dazzling features are often the most ephemeral, then the act of looking, patient, precise, and reverent, is itself a moral act. It honors the smallness of human presence against the sweep of cosmic time by turning attention into knowledge. Saturn, with its ancient storms and luminous, fragile rings, thus becomes both an object of scientific interrogation and a mirror. When the question is posed, is there a solid heart under the deep atmosphere or an ocean without shore? The answer is less a line in a definitive ledger than an invitation to continue reading, to keep refining instruments, to follow the slow accrual of evidence, and to accept that some planetary truths emerge only in the patience of repeated glances. Across centuries, the planet's pages are open. They are waiting for readers who can endure the scale of deep time. What is the origin story of a planet's halo, the thin bands of debris that circle it like an annotation in a margin? Were those rings once shards of a satellite, pulverized by collision and turned into dust? Or are they the stubborn crumbs of a primordial circumplanetary disk, the leftover sediment from the moment when a giant planet was still accreting in a nursery of ice and rock? For Uranus and Neptune, the so-called ice giants, this question is not merely an exercise in cataloguing curiosities. It is a probe into the processes that sculpted the outer solar system: collisions and captures, gentle accretion and violent disruption, a history written both in slow chemistry and sudden catastrophe. Uranus and Neptune are cousins in mass and distance, but they read like different editions of the same book. Both are dominated, in bulk, by volatile-rich materials: water, ammonia, methane, the substances that astronomers once labeled simply as ices because, in the cold of their formation zone, they condensed and stuck together. Yet ice is a misdirection. Under the pressures and temperatures reached inside these planets, water and ammonia behave in exotic ways. Superionic phases in which oxygen atoms form a lattice through which hydrogen ions can flow freely, slurries that are neither solid nor liquid in the familiar terrestrial sense, electrically conducting layers that can sustain magnetic dynamos in unexpected places. These compositional differences, an interior more water-rich and less dominated by metallic hydrogen than Jupiter and Saturn, help to explain many of their peculiarities, including their families of moons and the faint filigree of rings. The rings themselves are modest, elegant, and dark. Uranus's system is a sequence of narrow, sharply bounded bands, discovered through the sharp cut of a star's light as Uranus passed in front of it, and populated by small shepherd moons that confine and shape the ring's edges. Neptune's rings are sparse and intriguing, the fragmented arcs and clumps turned up by Voyager 2 surprised observers who expected a smooth, continuous ring. These rings are not the broad, glittering sheets of Saturn. They are charcoal sketches, low albedo, rich in organic tholins and radiation-processed ices, and conspicuously fragile in dynamical terms. Two families of origin stories compete to explain such features. The first is violent and immediate, rings and many small inner moons of the detritus of shattered satellites. In this scenario, impacts with cometary or asteroidal bodies, or catastrophic tidal disruption during a capture event, grind the moon into fragments. Those fragments reprocess under the planet's gravity, spreading into a ring that may later accrete into shepherd moons or feed the planet with slow inward rain. The second is patient and conservative. Rings are relics of the circumplanetary disk, the remnant material that never accreted into large satellites during the planet's formation. In this view, rings and inner satellites formed in the same epoch as the planet's regular moons, with the surviving ring material being what was never swept clean. Both accounts find support in different lines of evidence. The narrowness and sharp confinement of Uranus's rings, together with the presence of nearby small moons, favor collisional or disruptive origins. Interactions between moons and rings, resonant shepherding, and recent collisions can maintain narrow rings. The location of some rings near the Roche limit, the distance within which tidal forces prevent solid bodies from coalescing, argues that fragmentation and tidal shearing can create persistent rings where larger bodies cannot form. Conversely, the composition and coarse grain sizes in certain rings are consistent with primordial material processed slowly by radiation over eons. Age estimates derived from micrometeoroid bombardment and ring particle darkening are ambiguous, they allow, for both young, continuously replenished rings and older, slowly evolving ones. The ambiguity itself is telling. The solar system keeps both thin stories and thick ones in its margin notes. Neptune offers a particularly vivid laboratory for thinking about disruption. The discovery of Triton, a large retrograde moon that orbits Neptune in the opposite direction of the planet's rotation, suggests a violent intervening chapter. Triton's orbit and composition are the fingerprints of a captured Kuiper Belt object. The tidal capture and subsequent orbital evolution of a body so massive would have been profoundly disruptive. Models show that such a capture would have destabilized any pre-existing regular satellite system, producing a surge of collisions and potentially creating a transient disk of debris. That debris could have accreted into the small inner moons we observe today or been ground apart into the faint rings. In that sense, Neptune's present satellite and ring architecture may be a direct palimpsest of an extraordinary encounter, a late arrival that rewrote the system and left the new handwriting still legible, though smudged. Uranus carries a different but equally evocative signature of violence, an axial tilt of roughly 98 degrees, a planet that rotates practically on its side. The simplest explanation invokes a major glancing impact in the planet's youth, a collision with a planetary embryo large enough to tip the spin axis and eject material into orbit. The debris cloud from such a strike could settle into a disk from which the inner satellites and rings would later reform. The architecture we see, inner satellites aligned with the extreme equator, rings sharply confined to the same plane, is consistent with a resettling after catastrophe. Yet the story is not neat. Uranus's interior thermal state is oddly quiescent. Unlike Neptune, it radiates little excess heat. If a colossal impact had delivered vast quantities of energy, why is Uranus's interior so comparatively cold now? Some models suggest that a violent collision could have injected angular momentum and rearranged thermal gradients such that heat is trapped in layers, delaying convective mixing and the release of internal heat for billions of years. That possibility folds the planet's ring and satellite origin into a broader question about long-term thermal memory, about how planets remember violence not only in their moons but in how they cool. Beyond these dramatic episodes, the ice giant's formation environment and subsequent dynamical evolution remain central to the debate. In classical models, the ice giant's icy, volatile-rich composition reflects formation beyond the snowline, where water and other volatiles condensed in abundance. Yet how they stopped accreting hydrogen and helium, becoming less massive than Jupiter and Saturn, is a subject of continuing inquiry. Migration of the giant planets during the early solar system rearranged the outer architecture, the so-called Nice model, and its descendants posit that exchanges of orbital energy among the giant scattered planetesimals, scattered nascent satellites, and injected comets into the inner system. Those migrations could have shepherded material into circumplanetary disks at different times, making the origin of rings a complex superposition of primordial leftovers and later debris. A crucial insight of recent decades is that the ice giant's interiors and magnetic fields are telling clues to composition and structure that bear directly on ring and satellite histories. Unlike Jupiter and Saturn, whose magnetic fields are largely dipolar and aligned with rotation, the magnetic fields of Uranus and Neptune are wildly tilted and centered away from the planet's centers. Such odd fields point to dynamos operating in shallow, non-central conducting shells, plausibly ionic oceans rich in water and ammonia under immense pressure, rather than in deep, metallic hydrogen layers. The region where dynamo action takes place, smeared into shells and gradients, echoes the idea that heavy elements within these planets are not neatly centralized but distributed. That distribution may have influenced not only the planet's magnetism but also tidal dissipation rates and the tidal interaction. Histories with satellites, how quickly moons spiraled inward or outward, how tidal heating waxed and waned, how collisions might have been damped. In short, internal structure informs orbital history, and orbital history shapes the rings. Observationally, the problem is data poor. Voyager 2's brief flybys remain the primary in situ encounters with both Uranus and Neptune. From those fleeting visits, radio occultations, magnetometer sweeps, imagery of rings and moons, astronomers stitched broad inferences but left many margins unfilled. Ground-based occultations, the Hubble Space Telescope, and infrared observatories have added layers, but the deepest questions demand long-term, close study, orbiters that map gravity fields, magnetospheres sampled over seasons, and high-resolution imaging of rings and embedded moonlets. The age of ring material, the flux of micrometeoroids, the rates of sputtering by charged particles, and the subtle exchanges between moons and rings, these are the empirical fulcrums on which the debate will turn. Proposed missions to return to Uranus and Neptune would be acts of patient reading, a willingness to let instruments spend years to decode the palimpsest. Speculative scenarios reach outward from these constraints. If Uranus's rings are the reconstituted remains of a post-impact debris disk, then their particles may be comparatively young, darkened rapidly by radiation and micrometeoroid weathering, and the inner moons would show a thermal and orbital relation that betrays common ancestry. If Neptune's rings are echoes of Triton's capture, then their architecture should bear the imprint of a transient chaotic era, irregular moon orbits, a distribution of sizes reflecting collisional cascades, and perhaps a measurable mixing of primordial materials with captured Kuiper belt chemistry. Conversely, if rings are largely primordial, then their composition should more closely match an expectation of circumplanetary disk chemistry, a gradient of condensates, shaped by temperature and pressure at the time of satellite formation, and the rings should show a slow, steady evolution consistent with long dwell times. The truth, as is often the case with planetary palimpsests, is likely braided. Catastrophes can overprint and rework primordial material. Primordial disks can leave behind crumbs that later collisions rearrange. Neptune's capture of Triton could have eradicated an older ring system and left a second-generation system in its wake. Uranus's tilt could have erased, then rewritten, its inner inventory. The ring systems we see today may be accumulative documents assembled from multiple episodes, an early circumplanetary residue, later collisional additions, steady erosion by dust, and intermittent replenishment by moon-moon interactions or cryovolcanic outgassing. Each mechanism writes in a different ink and on a different substrate. Collisions produce coarse fragments and high relative velocities. Primordial leftovers carry a compositional signature of the nebula, capture events, produce asymmetries, and retrograde survivors. Beyond the solar system, these uncertainties acquire an added purpose. Ice giants are among the most commonly detected classes of exoplanets in radial velocity and transit surveys. Worlds often classified as Neptunes or sub-Neptunes. The way their rings form, the resilience of their satellites, and the manner in which they remember collisional histories will matter for interpreting remote observations. Transit light curves shaped by rings, spectral signatures influenced by dusty halos, and magnetic interactions that modulate star-planet coupling. Understanding whether rings are temporary ornaments or enduring relics is thus not a parochial concern, but a key to reading distant planetary biographies. In the end, the debate about rings and satellites around Uranus and Neptune is a meditation on how planetary memory is encoded. Do we read a ring as evidence of violence, a violent crash that left a new margin of dust, or as residue of patient, ordinary accretion? The answer reframes the planetary character, a system dominated by chance encounters and erasures, or a system where the residue of formation is stubbornly preserved. The observational constraints currently allow both readings, and the most honest interpretation is a cautious one. These planets are archives without an easily legible index. Their rings and moons are marginal notes, layered, amended, sometimes overwritten. The proper posture for the listener, then, is both curiosity and humility. The ice giants teach restraint, that histories are seldom single-threaded, that physical processes leave overlapping signatures, and that the most elegant explanation must survive a gauntlet of alternative readings. A future orbiter's slow radial hum, gravity maps accumulated over months, and high-resolution ring imaging will not offer a single dramatic revelation so much as a steady accretion of marginalia. The kind of evidence that transforms speculation into narrative. Until that patient work is done, Uranus and Neptune will keep their secrets with a dignity befitting distant elders. Their rings, faint and dark against the cold blue and green of methanetin-tinted skies, will remain as enigmatic annotations. Are they the dust of broken moons, the residue of a childhood disk, or both? The question is both technical and existential. It asks how violence and time conspire to shape memory, how creation and destruction become entangled in a planet's margins, and how the slow, attentive craft of observation can, across decades and missions, begin to read what was once thought unreadable. In that endeavor, the ice giants are not just distant objects of study, but teachers in the art of patient interpretation. Gentle instructors that remind the reader of the world's long habit of writing, erasing, and then offering, in faint lines, the traces of what once was. A single image opens the question, a planet steeped in a surreal, deep blue, its atmosphere streaked with bands and spirals that trace winds faster than any storm humans have seen. Why, the inquiry asks, would two distant siblings of the outer system, worlds born from the same protoplanetary dust, tilt their rotational axes and set their atmospheres roiling with supersonic gusts? It is a question that begins with color and ends in the tangled ledger of deep time. A question that forces a listener to consider not only the visible weather, but the invisible ledger beneath the clouds, internal heat, ancient collisions, subtle chemistry, and the slow memory of formation. The blue tone is not merely decoration. Methane, a minor constituent by mass, but an avid absorber of red light, eats the long wavelengths and leaves the shorter, bluer hues to scatter back to the eye. That simple molecular preference is the first clue. The appearance of a planet is often a cheap door into its composition. But the deeper mysteries are mechanical and historical. The outer ice-rich giants spin rapidly, host internal regimes where water and ammonia behave like strange fluids, and in at least one case, Neptune, throw off more heat than they receive from the sun. These are not static baubles, they are engines. Axial tilt, when it is extreme, is almost always a fossil of violence. Uranus's rotation, nearly on its side at roughly 98 degrees, reads like a margin note that says, here, something happened. The simplest, most compelling reconstruction of that event is a late, massive collision, a planetary marriage gone wrong, an impact with an embryo substantial enough to flip the spin axis and fling material into orbit. The tilt is itself a preserved outcome of chaotic youth. The aftermath is not merely a mechanical oddity, it sculpts the subsequent climate and dynamics. A pole that faces the sun for decades bathes one hemisphere in a prolonged summer. Decades later, the same pole slides into an uncompromising winter. Such extreme seasons change the way energy is input at the boundaries and, in turn, how the atmosphere responds. But tilt is not the whole story. winds on the ice giants are stupendously fast. Neptune displays the most vigorous zonal jets in the solar system, with speeds sometimes measured in kilometers per second of atmospheric motion relative to local fluid sound speeds. What drives such ferocity? The listener must think in terms of energy budgets. On Earth, solar insolation and the uneven heating of the surface drive the weather. For the outer giants' internal heat, the planet's residual thermal energy from formation and from slow contraction often dominates. Convection driven from the interior rises into the atmosphere and, set into the rotation frame of a rapidly spinning sphere, those upwellings are sculpted by the Coriolis effect into strong banded jets. The number, speed, and latitudinal placement of those jets are controlled by scales where rotation and turbulence meet. Physics of Rossby waves and Rhines, scaling familiar to fluid dynamicists but daunting in the planetary context. There is a further, sharper paradox. Uranus is comparatively lethargic in emitted heat, while Neptune belches out far more than it receives. Why would two apparent cousins diverge so dramatically? Here the story splits into possibilities that are not mutually exclusive. A giant impact can explain Uranus's tilt and, perhaps, a suppression of convective heat loss. If a late collision scrambled the internal gradients or introduced compositionally distinct layers, the convective plumbing of the planet could be altered, effectively insulating parts of the deep interior and keeping heat bottled up. Neptune, by contrast, may have escaped such tamping and therefore continues to convect vigorously, feeding stronger atmospheric turbulence and faster winds. Another possibility is compositional stratification, gradients in molecular weight that inhibit larger-scale convection by creating stably stratified layers. When mixing is difficult, heat leaks out slowly. When mixing is easy, it powers enormous atmospheric motions. Magnetic fields add their own strange flourishes to this account. Unlike the largely axial dipoles of Earth and Jupiter, the ice giants sport odd, multipolar magnetospheres offset from their centers. Such fields are most naturally generated not in a deep metallic hydrogen layer, but in the shallower, electrically conducting shell, plausibly an ionic ocean of water, ammonia, and salts under enormous pressure. Those dynamo regions, displaced and irregular, speak again of non-trivial interior structure. The heavy elements are not all stacked in a compact core, but are distributed in gradients. The same interior that bends magnetism may also modulate heat transport and contribute to the vigor of atmospheric jets. In short, the tilt and the winds are not separate curiosities but interwoven marginalia on the financial ledger of planetary formation. A world spin axis, internal layering, dynamo, and weather are all sentences in the same paragraph. This physical complexity is one of the reasons the narrative moves outward to consider the satellites that accompany these planets. The outer planets do not travel alone. They are circled by moons whose variety reads like a compendium of possibilities. And within that menagerie lies some of the most provocative pages of the planetary palimpsest. Icy shells that hide global oceans, plumes that spew frozen water into space, and compositions that whisper of chemical richness. The title of this next chapter is simple and enormous: The Moons and Strange Satellites. Europa and Enceladus occupy a special place in that chapter. They are small worlds with big claims. Beneath brittle ice, they guard expansive liquid water. Oceans that, in volume and perspective, can exceed the water content of all of Earth's surface seas combined. Yet these oceans are not placid. They are heated by tides, the perpetual flexing of their interiors due to gravitational embraces with their giant neighbors and resonant companions. That mechanical energy is converted into heat where the rock resists deformation or where the ice shell grinds and slips. In the case of Enceladus, it is concentrated near fissures known as tiger stripes, where fractures let warm material escape and drive geysers that launch jets of vapor, ice grains, and organic molecules into space. Cassini flew through those plumes, tasted their chemistry, and returned data that upended modest assumptions. Water vapor laced with salts, complex organic molecules, and a surprising inventory of hydrogen, the latter a plausible signpost of hydrothermal activity at a rocky seafloor interacting with circulating ocean water. Europa tells a parallel but distinct tale. Seen through Galileo's instruments, Europa's skin is a tapestry of intersecting cracks, braided ridges, and regions of disrupted ice, chaotic terrains that seem to be places where ice has been churned, melted, and refrozen. Induced magnetic signatures measured during flybys argue for a conducting layer beneath the shell, a saltwater ocean. Spectroscopy finds non-ice materials on the surface, likely salts or sulfuric derivatives, hinting at exchange between the ocean and the ice above. There are also tantalizing, though still debated, observations of plume-like activity from Hubble Space Telescope images, a suggestion that, like Enceladus, Europa occasionally vents oceanic material into space where it can be sampled remotely. The scientific significance of subsurface oceans is not merely abundance, it is the possibility of persistent energy and chemical disequilibria, the very conditions required for metabolism as life is, known to exploit it. On Earth, the richest life at the limits is found in places of flux hydrothermal vents where hot, reduced fluids meet cold seawater rich in oxidants, creating redox pairs that microbes can harvest. The same physics, hydrogen production by water-rock reactions, serpentization of ultramafic rock, the creation of gradients in pH and chemical potential, could obtain at the ocean-to-sea floor interface on these moons. The chemistry of Enceladus's plumes, including micron-sized silica grains and molecular hydrogen, is consistent with water interacting with hot rock at high pressures, an oxygen-poor, hydrogen-rich scenario that supplies energy potential for life. Yet the story is as much about preservation as it is about origin. Ice is an excellent archive in some respects. It can trap organics, sequester them from radiation, and, when reworked in layered deposits, preserve stratigraphic records of past chemistry. Plumes provide a rare, practical advantage for remote investigation. They eject material directly from the oceanic reservoir into space, bypassing the need to drill through kilometers of ice. Sampling a plume is the scientific equivalent of finding a torn page that someone has tossed into the aisle for inspection. Cassini's plume samples on Enceladus were a revelatory margin note. Future missions may expand that book. The evidence, however, is probabilistic and humble. Detecting organics in a plume or a spectral fingerprint on a surface is not, by itself, proof of biology. Abiotic chemistry can build surprisingly complex molecules under the right conditions. The challenge is to find patterns that are unlikely to arise without metabolism, isotopic fractionations, molecular distribution showing an improbable bias, ensembles of compounds that fit biochemical pathways better than geochemical ones. Equally important is demonstrating sustained energy fluxes and redox couples sufficient to support metabolisms over geologic timescales. That is a higher bar than finding one molecule in a sample. Other moons add texture to the argument. Titan, with its dense nitrogen atmosphere and seas of methane and ethane, offers a chemically exotic laboratory where prebiotic chemistry might run on hydrocarbon solvents rather than water. Ganymede's intrinsic magnetic field and suspected layered oceanal structure, Callisto's battered and ancient surface, Io's inferno of volcanism, each satellite carries a different set of physical and chemical chapters. Together, the moons are a catalogue of outcomes. Some worlds debug geological memory by constant resurfacing. Others preserve ancient histories in a frozen record. They demonstrate the variety of ways that water, heat, and chemistry can arrange themselves. The instruments that read these pages are diverse. Magnetometers that reveal induced signals, radar sounders that map ice thickness, mass spectrometers that sample plume particles, infrared spectrometers that infer salts and organics, and gravity mapping that constrains internal structure. All of these are different lenses for the same underlying interrogation. Planned missions, such as Europa Clipper and ESA's JOICE, are designed with that multi-instrument philosophy to map surfaces, sample exospheres, and deploy radar to probe the ice. There are also proposals for landers and cryoborers that would attempt to access near-ice surface ice or even shallow liquid pockets. Each approach carries technical, financial, and ethical constraints. Planetary protection looms large. The risk of contaminating an environment that might be habitable demands extraordinary cleanliness and care. Emotion threads through the technical narrative. There is the perennial human sensation of smallness, the recognition that vast oceans teeming with potential chemistry are hidden beneath thin skins of ice tens to hundreds of kilometers across. There is also the humility of epistemology, that great claims about life require patient, multidisciplinary corroboration, and that the archives are noisy and ambiguous. The desire to read the pages quickly is often tempered by methodological caution. The stakes, both scientific and philosophical, are high. Finding life in a subsurface ocean would not only recast the biography of that moon, it would lift the veil on the probability that life arises wherever conditions allow it, altering the conceptual structure of habitability across the cosmos. Finally, The story returns to a motif that has been present since the opening meditations: palimpsest and patience. The blue swirl of an atmosphere and the jagged, ethereal jets from a moon's south polar fissures are both marginalia. They are not ultimate answers, but hints along a long, patient reading. The tilt and wind of an ice giant record formative violence and internal memory, the plumes and chaos terrains of moon's record, exchange and potential habitability, both kinds of evidence reward a humility of interpretation, the courteous and careful assembly of many marginal clues into a constrained narrative, always conceding to uncertainty. For the listener, the moment is not closure, but invitation. There are places in the solar system where oceans breathe quietly under ice, where energy flows are subtle and ancient, where molecules are recycled and held in store. The task ahead, to sample, to map, to model, is at once profoundly technical and deeply existential. The question of why two distant cousins tilt and roar, and why small satellites hide oceans, are the same kind of question. They demand an attention to scale, to history, and to processes that operate far beyond human lifespans. In answering, slowly and with care, humanity learns not only the physics of planets and moons, but also how to be patient readers of a cosmic book whose margins are rich with suggestions and whose central text still hides many sentences yet to be deciphered. What would it mean, the narrator asks, if life's chemistry were not shackled to the thin sliver of habitability defined by liquid water at Earth-like temperatures? What if, elsewhere in the same system that cradles us, a different set of physical rules had permitted an alternative tapestry of chemistry to assemble, persist, and perhaps even tinker toward biology? That question opens the possibility of a second Genesis, not a repetition of Earth's story, but a wholly other experiment, one run on methane, sculpted by cryogenic logic. The image that arrests the imagination is simple and stubborn: rivers that run dark and slow, not of water, but of methane. The largest of these liquefied lanes is found on Titan, Saturn's enigmatic moon, a world that in many ways reads like a draft imagining of Earth rewritten at 79 degrees C. Titan's surface hosts lakes and seas at its poles, channels that braid and meander, deltas that fan into basins, and shorelines that shift subtly under seasonal solar pressure. The discovery of fluvial networks and shorelines was not merely surprising, it was revolutionary. It expanded the definition of planetary hydrology. On Titan, methane and ethane play the hydraulic role that water plays on Earth. They evaporate, condense into clouds, fall as precipitation, flow into basins, and carve the landscape over geologic time. That hydraulic cycle is coupled to a rich atmospheric chemistry. The thick orange haze that cloaked Titan is not cosmetic. Ultraviolet light from the sun and energetic particles from Saturn's magnetosphere drive a photochemical factory in the upper atmosphere. Simple molecules, nitrogen and methane, are stripped, recombined, and polymerized into complex organics. The resulting soot-like compounds, often referred to as tholins, rain down to the surface, blanketing dunes and shores with a tarry residue. Where Earth's skies nurture rain that scrubs and renews, Titan skies build and deliver a steady inventory of organic complexity. The surface thus becomes a chemical workshop, where long, carbon-rich chains accumulate under frigid conditions, creating a repository of molecular precursors that, on Earth, would be called prebiotic. The possibility of life on Titan is not merely a matter of exotic romance. It is a disciplined hypothesis that rearranges the canonical checklist: solvent, energy source, and chemical disequilibrium. Titan provides solvent, but the solvent is methane and ethane, liquid at its surface temperatures. It supplies abundant organic molecules. The sticking point is energy. Chemistry at cryogenic temperatures is slow. Reaction rates drop precipitously as thermal motion wanes. Without sufficient fluxes of usable energy, complex chemistry stalls. But Titan is not energetically inert. Photochemical processing in the atmosphere produces reactive species, surface radiation, and lightning, hypothesized, though unobserved directly, could generate local hotspots. Cryovolcanic activity, if present, may inject warmth and subsurface fluids into the shell, and tidal interactions, however weak compared with inner icy moons, may produce localized heating. The combination of these processes opens plausible niches where non-trivial chemistry could persist. More than plausibility is required for the bold claim of a second Genesis. What would an organism on Titan use for membranes, for catalysis, for metabolism? Here the literature of the speculative and the experimental converges. Laboratory work has suggested the possibility of stable, membrane-like structures forming in liquid methane, so-called azotosomes, composed of nitrogen and containing molecules that could form vesicle-like compartments at cryogenic temperatures. Such structures, if stable and capable of compartmentalizing chemistry, would offer parallel to the lipid bilayers that cradle terrestrial life. Metabolic analogues are being proposed as well, chemistries that exploit redox gradients between available species, or that use catalytic mineral surfaces to lower activation energies. In short, the conceptual scaffolding for non-vacuous life exists, even if its experimental realization remains incomplete. There is an added, tantalizing dimension to Titan's habitability debate. The moon's interior may harbor liquid water. Radar and gravity measurements, coupled with theoretical modeling, indicate a likely subsurface ocean sandwiched beneath an ice shell. That ocean, warmer by planetary standards, could be the site for water-based life or, at minimum, for chemically active interfaces between rock and liquid that generate energy-rich compounds. The coexistence of a surface rich in organics and a hidden aqueous reservoir is a potent combination. It creates the possibility of exchange if cryovolcanism or impact events transport organic-rich materials downward, or if subsurface plumes convey water upward. Environments of mixed chemistry could form, interfaces where water and hydrocarbons meet, where temperature gradients are strong, and where catalysis may be surprisingly efficient despite the cold. These hybrid zones are the planetary analog of ecological ecotones, places that, by virtue of being transitional, are often fertile cradles of innovation. Yet the scientific mood when discussing Titan is appropriately cautious. Titan's hydrocarbons and tholins are chemically appealing and striking. They are not, by themselves, biosignatures. Organic complexity can be formed abiotically given enough time and the right energy inputs. Distinguishing a strange biochemistry from robust abiotic synthesis requires multiple convergent indicators, molecular patterns that reflect metabolism rather than random polymerization, isotopic fractionations that favor light isotopes in ways coherent with biological processing, or enantiomeric excesses that suggest a chiral bias beyond stochastic assembly. Detecting such signals on Titan's surface demands direct sampling, context-rich analyses, and, crucially, an understanding of how non-living chemistry could mimic biological patterns in a cryogenic milieu. The methodology for that search is not merely hypothetical. Mission concepts and planned explorers have been designed with these very questions in mind. The Dragonfly mission, for example, envisions a rotorcraft lander that will traverse Titan's diverse terrains, sampling dunes, impact deposits, and possible shorelines. It will carry instruments capable of mass spectrometry, chromatography, and imaging, tools to read the moon's chemical palimpsest. In parallel, laboratory experiments replicate Titan's conditions to see which molecules and structures are plausibly formed without life. The approach is forensic. Propose hypotheses about abiotic chemistry, test them experimentally, and design missions to seek departure from those expectations. Enceladus and Europa remain, in the broader search for life in the solar system, the strongest candidates for water-based biologies. Their plumes and induced magnetic signature supply the most accessible glimpses of subsurface oceans. To the extent that Titan's surface invites the hypothesis of non-aqueous life, Enceladus and Europa invite a different, perhaps more familiar, inquiry. Is there life in the dark, pressurized seas warmed by tidal heating? The answers across these moons are complementary. Titan shows that habitability can be reimagined in solvent space. Enceladus and Europa show that habitability is not exclusively a surface story, but a subsurface affair. Together they expand the map of possibility. The investigator's posture in all of this is shaped by epistemic humility. Every candidate biosignature must be filtered through a crucible of alternative explanations. The planetary record is noisy. Chemical systems can converge on complexity without living agents. The inquiry must be disciplined, accumulating evidence across multiple dimensions, molecular, isotopic, mineralogical, and contextual. And yet the emotional tenor, the sense of wonder, the thrill of possibility, is essential fuel. Science advances by disciplined imagination. The hypothesis of a second genesis, whether ultimately confirmed or refuted, reshapes the methodological tools used to read planetary archives. This thread, the patient, cautious extrapolation from observables to possibility, leads naturally outward, beyond the confines of the solar system. If a moon like Titan can host liquid hydrocarbons and complex organics, Then the diversity of worlds in the galaxy suggests that nature's laboratory is far broader than once imagined. The catalogue of known exoplanets is no longer the handful of oddities detected in early surveys. It is a burgeoning library, thousands of confirmed worlds, and counting, each a different experiment in mass, composition, orbital architecture, and stellar environment. The discovery of these planets has altered the terms of the question. Where once the focus was on finding Earth analogues by distance from a star, the community now recognizes that habitability is a multi-dimensional condition. Planets called super-Earths and mini-Neptunes dominate size distributions, hot Jupiters, gas giants orbiting perilously close to their stars, challenge formation models, tightly packed systems of multiple terrestrial-sized planets show architectures absent in our own backyard. Observational selection effects once biased the record, but current missions and instruments, transit surveys, radial velocity arrays, direct imaging, and high-resolution spectroscopy increasingly reveal a genuine diversity that forces a change in imagination. More than sheer numbers, the methods of detection and characterization have matured. Transmission spectroscopy, in which starlight filters through a planet's atmosphere during transit, allows scientists to probe molecular signatures, water vapor, methane, carbon dioxide, metal oxides, and clouds. Instruments such as the James Webb Space Telescope extend this capability into the infrared, where many molecular fingerprints are most conspicuous. Direct imaging, although challenging, can isolate light from young, self-luminous planets or from planets at large separations, enabling studies of atmospheric composition and dynamics. Radial velocity measurements give mass constraints, and combined mass-radius measurements yield average densities, rough proxies for composition and possible internal structure. These tools open the possibility of seeking biosignatures at interstellar distances. The logic is anchored in disequilibrium. Life maintains chemical states that, absent continuous replenishment, would relax toward equilibrium. On Earth, the simultaneous presence of oxygen and methane at appreciable levels is a dramatic example of such disequilibrium, sustained largely by biological activity. Translating that logic to exoplanets requires nuance. Oxygen can accumulate abiotically under certain conditions, for example, via photodissociation and hydrogen escape, and methane can be produced abiotically by serpentinization and other geochemical processes. Thus, the search for life remotely becomes an exercise in constructing robust falsification frameworks, which combinations of molecules in which planetary contexts are unlikely to be produced and maintained without biology. How might surface conditions, stellar type, and volcanic fluxes mimic biosignatures? The endeavor is both subtle and exacting. Beyond biosignatures, the exoplanetary census reframes questions about the frequency and variety of potentially habitable environments. If super-Earths are common, do they possess thick hydrogen envelopes that preclude life as we know it? Or can some have thin atmospheres and temperate conditions? If tightly locked planets orbiting meddwarfs are abundant in the habitable zone, can atmospheric circulation mitigate extreme day-night contrasts and sustain climates compatible with liquids? The answers will shape not only the probability calculus of life's existence, but the design of future missions. Yet, with breadth comes epistemic caution. The habitability of an exoplanet cannot be settled by a single parameter. Atmosphere-surface coupling, geologic activity, magnetic shielding, stellar variability, and volatile history each play decisive roles. The search thus becomes a synthetic enterprise, combining population statistics, targeted observations, laboratory studies of exotic chemistry, and theoretical models of climate and interior dynamics. It is, in essence, an extension of the palimpsest reading practiced in the solar system, scaled up to stellar neighborhoods and constrained by slender spectral lines. The human reaction to this widening vista is complex. On one hand, the abundance and diversity of exoplanets are intellectually invigorating. They suggest that planetary experimentation is a cosmic norm, not a rare fluke. On the other hand, the lack, so far, of a clear biosignature beyond Earth keeps humility in the foreground. Each new detection, an atmosphere with water vapor, an unexpected abundance of methane, a planet with the mass of Earth but an inflated radius, is both a potential marginalia and a cautionary footnote. The methodological posture remains: imagine boldly, test rigorously, and concede uncertainty as a permanent element of the inquiry. Thus, the narrative arc from Titan's methane rivers to the tides of exoplanet discovery is not a shift from specificity to abstraction, but a continuum of the same practice, reading natural archives for signs of organized chemistry and, possibly, life. Titan embodies a radical lesson that solvents, temperatures, and chemistries once deemed improbable for biology may nonetheless host rich prebiotic and potentially biotic processes. The exoplanet catalogue amplifies that lesson. The universe offers conditions far more varied than the narrow Earth-centric window. The proper response is neither anthropocentric urgency nor passive resignation, but a patient, methodical expansion of the search, guided by theory, grounded in laboratory tests, and executed with missions that can collect the faint, contextual evidence necessary to adjudicate competing explanations. A mystery remains open and electrifying. Are Titan, Enceladus, Europa, and the tens of thousands of exoplanets simply laboratories of chemical complexity, or do any of them bear the unmistakable signature of a second life, a life independent of Earth's lineage? The question is not only scientific, it is philosophical, ethical, and existential. It reshapes humanity's sense of contingency and kinship in the cosmos. Answering it will require the patient accumulation of marginalia, the careful reading of planetary palimpsests, and an imagination disciplined by method. The search, in that sense, is the story, not simply the discovery of another life, but the persistent, reverent attempt to translate faint, epochal inscriptions written in the slow grammar of worlds. Which of the thousands of worlds now catalogued in a night does the long, patient work of becoming a cradle for intelligence? The question sits at once simple and insoluble. Simple, because it can be phrased in a sentence. Insoluble, because it folds together chemistry, geology, climate, time, chance, time, and the habits of energy flows into a single, multi-layered problem. In the last 2 decades, the catalogue of known planets has swelled from a curiosity to a census. Some of those newcomers resemble Earth in tantalizing ways, a similar radius, an orbit, and a temperate band, spectral hints of water vapor or carbon dioxide. Others are extremes that would have been dismissed as science fiction 3 generations ago. Worlds scorched to molten glass on their day-sides, tidally locked planets with a permanent twilight line, ocean-covered super-Earths whose every map would be a single unbroken blue, and methane seas under alien skies. The diversity is not merely an inventory, it is a rhetorical challenge to notions of habitability that were once comfortably Earth-centric. The emotional register of this discovery is itself a kind of data. There is awe, an almost trembling pleasure at discovering architectural variety in planetary formation. There is exhilaration. Each new detection is a marginalia in a book that readers thought was finished. And there is a persistent, heavier feeling, doubt. That doubt is not despair but caution, a recognition that seeing a planet is not the same as reading a life history. Telescopes can measure size, bulk, density, orbital period, and, with growing sophistication, aspects of atmospheric composition that cannot, at least not directly, read the slow ledger of geological recycling, the history of impacts, or the long arc of climatic stability. To ask whether a planet could nurture intelligent life is therefore to ask not only about present conditions, but about ecological trajectories through deep time. The field has responded with a catalogue of filters, heuristics meant to sort worlds into buckets of plausibility. Distance from the host star remains a crude but useful first pass, a temperate band where liquid solvents can exist on a surface for at least some fraction of a planet's orbit. Mass and radius constrained bulk composition. A very low density suggests a volatile, rich envelope that may preclude a solid surface an excessively massive world could crush any would-be biosphere beneath extreme pressures. Stellar-type matters. Maw-dwarfs are ubiquitous and host many detected Earth-sized planets in their habitable zones, but their proclivity for flares and the prolonged youth of their magnetic tantrums makes long-term atmospheric survival a stake in the ground. Rotation, axial tilt, and orbital eccentricity carve the climatic rhythms that would condition any evolving intelligences. Seasons and social pacing. Above all, longevity, the capacity of a world to remain in a habitable window for hundreds of millions to billions of years, emerges as the crucial variable for any scenario that imagines intelligence as a late-shoe arising bloom rather than an immediate bloom. None of these filters is decisive. They are probabilistic needles in a haystack of planetary histories. A planet in the temperate band around a mid-dwarf may orbit under relentless flares, yet shield its atmosphere through an unexpectedly strong magnetic field. A super-Earth with a deep volatile envelope may nonetheless host a shallow, habitable surface, if atmospheric loss thins it over eons. The palette of possibilities is wide, and the observational biases are stubborn. Current detection methods favor short-period planets and those that produce large signals. These are often not the most clement places for life to mature slowly. The result is an asymmetry between what is easiest to find and what would be best for fostering complex cultural evolution. The question of intelligence introduces additional conceptual complexity. Intelligence on Earth is the product not merely of biochemistry, but of a prolonged interaction among geology, climate, and ecology. The ascent of tool-using hominins required stable, shallow continental shelves, seasoned the concentrated resources, landscapes that encouraged planning and social learning, and a suite of chemical and energetic flows that allowed ecosystems to support large, ek-brained, slow-reproducing animals. If one attempts to generalize, certain features recur: environmental heterogeneity on spatial and temporal scales that reward innovation, persistent energy gradients that can be harnessed by living systems, and a planetary memory, processes such as plate tectonics and atmospheric regulation that prevent catastrophic swings on timescales shorter than the development of cumulative culture. Those are plausible conditions, but not axioms. The idea that continents and plate tectonics are necessary is persuasive because they promote nutrient recycling and long-term climate stability, but it remains possible that alternative architectures could head toward intelligence. An ocean world with hydrothermal gradients at a rocky seafloor and abundant chemical energy could sustain complex life without exposed land. A tidally locked world with a permanent twilight belt might host stable climate niches along its substellar terminator. Titan-like chemistries open the door for completely alien evolutionary experiments. The problem is not one of imagination, but of evidentiary weight. Which architectures are not only possible, but probable, to produce the recurring features of long-term ecological richness and cognitive escalation? Crucially, the record of the planet itself is an unreliable scribe. Geological processes erase as efficiently as they record. Tectonics recycles crust, impacts bury and excavate, atmosphere and ocean chemistry homogenize and disguise. If intelligence arises and develops technology, its artifacts will be exceptions in the slow arithmetic of planetary erasure. The same processes that can obliterate a civilization's monument also complicate an external observer's attempt to detect techno's signatures. On Earth, a record of industrial activity, a stratigraphic spike in greenhouse gases, an anthropogenic layer of plastics and novel isotopes is glaring on human timescales but faint and diffuse in geological ones. Extend that observation across millions of years and the signature becomes ambiguous. Thus, the search for intelligence must account for both the detection probability and the longevity of technosignatures in a diverse planetary set. Detection strategies have therefore broadened. Astronomers look for biosignatures in atmospheric compositions that are out of chemical equilibrium, combinations of oxygen and methane, for instance, while being acutely aware of abiotic pathways that can produce similar spectra. Technosignatures expand the palette further: narrowband radio emissions, megastructures inferred from peculiar transit light curves, artificial illumination of night sides, and industrial gases that cannot plausibly be produced geologically. Each class of signal carries both promise and the burden of alternative explanation. False positives are plentiful. The universe is a good mimic. False negatives are equally possible. Civilizations might choose to be quiet, migrate to subterranean refuges, or simply be shorter-lived relative to the cosmic clock. All this points to a reframing. Instead of searching for a single, definitive planet where hypothetical intelligence must arise, the scientific posture becomes probabilistic and pluralist. Planets fall on a spectrum of aptitude. Some look Earth-like in many respects. Others present extreme conditions where life, if it exists, would do so on utterly different terms, and yet others occupy middling positions where intermittent habitability could allow life to appear, die back, and reappear. The mystery, then, is not only which planet can support intelligent life, but how often the confluence of conditions that favor long-term cognitive evolution actually occurs in nature. Is intelligence an inevitability given a stable, habitable environment for a few 100 million years? Or is it a highly contingent, fragile event that requires a narrow set of planetary contingencies? The answer remains open. Statistical inference from the exoplanet census hints at abundant opportunities for life to start, but the jump from microbial complexity to tool-making societies may be where the rarity sits. In deep time, the evolutionary experiments are many. The surviving examples may be few. The human experience of intelligence, its aesthetic ethical and technological consequences, colors how the question is asked. Observers naturally project a kind of cosmic loneliness onto the possibility of rarity and a thrilling optimism onto the possibility of abundance. Both are, in the end, emotional hypotheses forged by limited data. Yet this openness is not a failure. It is the scientific texture of the problem. The right response is a method of patient accumulation. Refine instruments, broaden search strategies, couple observational surveys with laboratory simulations of exotic chemistries, send missions to sample atmospheres, plumes, and icy shells, and develop theoretical frameworks that can evaluate how different planetary systems sustain chemical disequilibria over geological timescales. Each approach is an act of careful reading, a way to distinguish smudges from letters in a palimpsest. There is also an ethical dimension that threads through the inquiry. Choosing which worlds to probe most intensively, how to avoid contaminating potential biospheres, and what it would mean to contact or detect another intelligence are questions that mingle science with moral imagination. The discovery of life, microbial or intelligent, would be a pivot in human self-understanding, reshaping narratives about uniqueness and kinship in the cosmos. The possibility that Earth's fragility might not be unique humbles the impulse to expansion without care. The prospect that Earth is singular intensifies the responsibility of stewardship. Either outcome reframes human priorities. So the curriculum of exploration shifts from a quest for a single answer to the cultivation of a long habit, patient observation, methodological humility, and an acceptance that many planetary stories will remain fragmentary. The reader of planetary palimpsests learns to value small margins, a suspicious isotope ratio, a seasonal variation in methane, a plume of icy grains where the noise is low enough to taste organics. Each marginalia, when corroborated across methods and timescales, becomes part of an emergent narrative. The trajectory of discovery is incremental, episodic, and often disappointing, but cumulatively transformative. The final, and perhaps most human, reflection is this: the search itself changes those who undertake it. The act of reaching outward, building instruments that translate faint photons into meaning, training minds to entertain multiple plausible histories, designing missions with planetary protection in mind, reshapes social institutions and ethical horizons. The cosmos becomes not just an object of speculation, but a partner in a long conversation about survival, curiosity, and care. Whether the question of another intelligent world resolves into a single discovery, a slow accretion of microbial signals, or the persistent silence of a universe crowded with sterile beauty, the journey continues. The Book of Worlds remains open. Pages will be turned at the pace of technology and patience. New marginalia will appear as spectra sharpen, as probes plunge into plumes, and as gravitational whispers yield interior structures. And with each marginal note, human understanding will grow less like certainty and more like a contour map, tentative lines, shaded regions of probability, corridors of plausible history. The journey toward knowing which planets can truly nurture intelligence is, by necessity, a journey without closure, a long, careful odyssey through palimpsests written in stone, ice, and gas. In that refusal of finality, there is consolation. To read slowly is to honor time itself. The mystery of where intelligence might flourish is not a riddle that demands an answer. Now it is an invitation to a prolonged attention, a practice of curiosity that measures itself in decades and centuries. The cosmos, patient as ever, will keep its pages. The human task is to keep reading, to sharpen instruments and questions, to avoid the arrogance of premature conclusions, and to hold the humility that deep time insists upon. The journey is not a search for a terminus, but a cultivation of wonder, an ethic of listening that may, one day, be rewarded with the faintest of replies from the margins of a distant world. What if the point was never to reach a tidy answer at all, but to be invited into an ever-widening conversation? That is the quiet insistence that gathers at the end of the long book the narrator has been reading, a slow, multi-voiced manuscript written in ice and basalt, in magnetic whispers and sulphurous clouds. Each planet, every moon and ring, presents a problem that yields traces rather than conclusions. The more carefully it is scrutinized, the more marginalia appear, anomalies that suggest new hypotheses, small contradictions that require new instruments, and patterns that braid natural process with the faint possibility of agency. A puzzle does not close, it proliferates. And as that proliferation is not failure, it is the constitution of curiosity. Humanity reads these planetary palimpsests in several idioms at once. There is the language of measurement, spectra, isotopes, gravity harmonics, radar echoes. There is the language of morphology, channels, craters, scarps, dunes. There is the language of process, convection, escape, accretion, erosion. To these technical grammars is added a third, looser voice, the human mind pointing and asking, how did this come to be? What could have been? That combination of rigor and wonder is what turns a data point into a question that matters across centuries. The fundamental recognition is simple and disciplined. Planets keep their memory in many registers, and those registers are fragile. A city's geometry can be erased by meters of sediment. Isotopic anomalies can be smoothed by mantle mixing. Chlorinated organics can be broken apart by ultraviolet light over millions of years. Deep time has tools of erasure that are efficient and indifferent. Yet obliteration is rarely absolute. Chemistry leaves ghost lines. Unusual abundances linger like odd punctuation. Structural anomalies resist the ocean's appetite for uniformity. The detective work, then, is not a hunt for obvious artifacts, but a patient exercise in probability, an archaeology of signatures. That method is the humbling core of the inquiry. It demands a particular temperament. First, obsession with marginal clues, a faint deuterium enrichment, an unexpected ratio of rare earth elements, a regularity in a remote radargram. Second, the willingness to imagine plausible alternative histories that could produce such signals. Volcanic pulses versus biological metabolism, photochemical escape versus industrial effluence, tidal heating versus radioactive decay. Third, a fierce compulsion to test those ideas with instruments designed not to confirm but to discriminate. Instruments are thought incarnate. They embody the questions that a community considers most pressing. Over and over in the survey of worlds, a recurrent paradox surfaces. The very processes that create complexity also erase its visible traces. Plate tectonics buries the earliest crusts even as it renews the conditions for long-lived ecosystems. Oceans preserve and then sequester organic strata. Atmospheric circulation records global chemistry in ice cores and then mixes it into indistinct hum, the consequence of the double humility. On one hand, the rare signs of prior habitability or intelligence, if ever present, may persist only in subtle geochemical or geometric fingerprints. On the other, the absence of obvious artifacts is no proof that nothing occurred. Silence in the margin is ambiguous. Human interpreters must therefore avoid both cavalier optimism and nihilistic dismissal. This ambiguity animates a specific kind of scientific architecture, one in which multiple, independent lines of evidence are required to raise a credible claim. A tantalizing chemical spike in an ancient sediment gains weight when matched to a corresponding isotopic shift, when the sedimentary context supports low energy deposition, and when alternative abiotic pathways are demonstrably unlikely. A speculative techno-signature is only useful if it survives scrutiny across physics, chemistry, and planetary dynamics. In short, the standards for extraordinary claims are deliberately high, not to deny wonder, but to ensure that wonder is anchored in the most careful reading the instruments can permit. The planets themselves teach different chapters of the same lesson. Mercury insists on contingency and accretion and the subtlety of nebular sorting. Venus speaks in a throatful of carbon dioxide about thresholds and runaway feedbacks, the fragile seams where climate regulation gives way to climatic lock. Mars keeps a long, halting record of hopeful rivers and abandoned basins, a testimony to transient habitability and the importance of planetary respiration, the coupling of interior and surface that sustains environments over geological time. The icy moons whisper of hidden seas and tidal craftsmanship. Their plumes and induced magnetic signatures are practical. Reminders that sometimes the most accessible clues lie in what is ejected outward. The gas giants and their rings demonstrate the planetary systems are not static backdrops, but active agents. Their migrations, resonances, and bombardments rearrange the very texts human explorers aim to read. That cascade of planetary lessons folds outward again to the crowded sky of exoplanets. The galactic census, now measured in thousands, has dispelled a comfortable anthropocentrism. Nature's experiments are manifold. Worlds exist that would have once been dismissed as impossible. Super-Earths with deep volatile envelopes, hot rocks whose dayside surfaces flow like glass, tidally locked planets cloaked in perpetual twilight. Each discovery reframes the notion of habitability from a single box on a checklist to a multidimensional manifold of possibility. The search for life, and for the rarer ascent of intelligence, becomes an exercise in boundary setting. Which combinations of composition, dynamics, and longevity produce the self-sustaining, innovation-enabling environments that may, under the right circumstances, yield complexity that reflects upon itself? Answering that question moves beyond instruments and into cultural choices. Which world should be sampled, and with what guarantees against contamination? What risks are acceptable in deploying drills or landers to a moon that may harbor a subsurface ocean? The missions now being planned embody a communal ethic as much as a scientific one. They are designed with planetary protection protocols, with layered verification strategies, with an eye toward avoiding irreversible disturbance. Science insists on rigorous cleanliness, not as an obstacle but as a moral posture. If life is found, even microbial, then the discovery's meaning will be entangled with the faithfulness of the search process. There is also a human psychology in the final act of reading. Curiosity has always pressed outward, a habit as old as tool-making. But the style of curiosity that planetary palimpsests demand is more patient, less consumptive. It is the appetite of a librarian rather than a looter, careful cataloging, cross-referencing, preserving context. Missions become long arcs of learning rather than quick triumphs. The best discoveries are earned through repeated passes, orbiters that watch seasonal changes year after year, landers that monitor weather and chemistry over decades, sample caches returned to laboratories decade after decade. Deep time insists that humanity's timelines grow longer, and yet that patience is energized, not numbed, by the scale of possibility. The absence of immediate answers does not shrink wonder, it amplifies it. Each marginal trace is a doorway. The detection of particular gases in an exoplanet's atmosphere is not a closed verdict, but a tide of questions. What geological processes generate those gases? Could biochemistry plausibly mimic them? Over what time scales would such balances persist? The interpretive enterprise becomes richer for its restraints. As instruments grow more sensitive, as missions reach further, and laboratories parse signatures at ever finer scales, the volume of marginalia will increase. This accumulation will not produce a single, conclusive paragraph about universal habitability, but will instead sketch contours, probabilities, and histories. One implication of that probabilistic outcome is an ethic of stewardship. The long view of planetary palimpsests enjoins a twin duty: to protect the integrity of other worlds as potential archives and to preserve Earth as an active, readable text. Earth's geological, chemical, and biological narratives are the most informative palimpsest humanity knows. They are also the only one that humans currently inhabit. To preserve the mostly subtle records of our species for future readers, whether human descendants or extraterrestrial visitors, demands sober reflection about waste, emissions, and cultural legacies. Similarly, to preserve extraterrestrial records demands restraints on exploration and an investment in technologies that minimize forward contamination. There is a different kind of stewardship too, epistemic stewardship. The search for life and for the signatures of past intelligence must avoid the twin errors of credulity and premature closure. The rhetorical seductions of dramatic claims, a mysterious radio burst, a spectral line that could be a biosignature, must be vetted by patient replication, open data, and a culture that rewards careful negative results as much as celebratory positives. The history of science is rich with episodes in which excitement outpaced rigor. Planetary palimpsests teach the value of a culture that prizes methodical verification. This is also a narrative of human transformation. The technologies built to read other worlds, cryogenic drills, ultra-clean sample lines, long-lived orbiters, high-precision photometers, are technologies that extend human patience and precision. They reshape society's temporal horizons. A civilization that designs missions across decades learns to think in generational time. It cultivates institutions that can preserve knowledge, funding, and craft across political cycles. The act of engaging with deep time externalizes humility. It trains societies to value continuity, shared goals, and a stewardship that reaches beyond immediate returns. And so the concluding page, or rather the open margin, returns to the original image. Each planet is a puzzle that invites more questions than immediate answers. That invitation is, in itself, an ethical summons. The mystery of a planet is not a threat, it is an opportunity. It calls humanity to refine instruments, to sharpen hypotheses, to invent cleaner tools, and to cultivate a discipline of patient curiosity. It nudges the species to reach beyond its comfort, not in a rush to conquer a new frontier, but to learn how to listen. If there is a final emotional pitch that the long study of planetary palimpsests leaves, it is a mixed one. Smallness and endurance braided together. There is the human sensation of being brief and local inside an immense chronology of matter and energy. There is, alongside that, the capacity to act across time, to design instruments that outlive individuals, and to encode questions in probes that will speak decades hence. That twin awareness of transience and responsibility is not a moral burden alone. It is a kind of exhilaration. It dignifies curiosity as a cultural project carried across generations. The mysteries of planets are therefore not puzzles to be solved in a single celebration, but invitations to a way of being. A long attention, meticulous and imaginative, that refuses trivial conclusions and accepts that some of the most profound answers will whisper rather than shout. To keep reading such marginalia is to cultivate a quieter ambition, to expand the human capacity for patient inquiry, to preserve fragile archives, and to let the questions multiply in the service of ever deeper understanding. The last sentence of this particular chapter may be a question, unclosed and generous. Will human curiosity prove steady enough to follow these faint signals across centuries, to translate smudges into narratives, and to accept whatever humility deep time imposes? The planetary book keeps its pages open. Its puzzles are invitations, not endpoints. Each answer discovered reframes the question, and each new question calls people, scientists, engineers, citizens together, to step beyond their limits and keep reading. In that ongoing enterprise, the mystery of a planet becomes the reason to continue, an endless, humane reaching toward the edges of what can be known,